imagine a red sky filled with memories. Stay here quietly, as we carefully uncover what that past might reveal. Tonight, we journey to a world that has captured human imagination for centuries. Mars, the red planet that hangs in our night sky like a distant ember, carrying secrets that span billions of years. As we begin this gentle exploration together, I want you to settle into comfort. This story weaves together scientific evidence with careful speculation. We will walk the line between what we know and what we wonder, always with respect for both discovery and mystery. The Mars we see today is a world of rust-colored deserts, of ancient canyons carved by forces we're only beginning to understand. But there was another Mars, a Mars that lived and breathed with different rhythms, perhaps for hundreds of millions of years. We know from rovers and orbiters, from careful analysis of meteorites that have traveled from Mars to Earth, that this world once held vast amounts of water. Rivers flowed across its surface. Lakes reflected alien skies. And in those waters, in that different climate, possibilities emerged that still whisper to us today. As we explore these possibilities together, remember that science requires both evidence and imagination. Tonight we honor both. We will clearly distinguish between what the evidence tells us as fact and what our careful reasoning suggests might have been possible. Let your breathing slow. Let your body sink deeper into rest. We are about to walk through time itself, back to an era when Mars sang with the sound of flowing water, when its atmosphere was thick enough to nurture complexity, when the ingredients for something remarkable were all present. This is not a story of certainties. It is a story of wonder guided by careful thought. As we move through each chapter, notice how the evidence builds, how possibilities emerge from data, how science and imagination dance together in the search for truth. Rest now. Let Mars come to you through these words, through this gentle journey into deep time. The red planet waits, patient as stone, ready to share its whispers with those who listen carefully. Chapter 1. The Mars that was. Water and climate. There was a time when red carried shades of blue, channels, deltas, and lake beds telling stories of water. Close your eyes and travel back 4 billion years. Mars is young then, still warm from its formation. The sun burns less brightly than today, but Mars holds its heat close, wrapped in an atmosphere thick with carbon dioxide and water vapor. The planet pulses with internal heat, volcanic systems breathing gases into skies heavy with possibility. Picture this ancient world. The sky is not the butterscotch color we know today, but deeper, richer, painted in shades of blue and gray, where water vapor condenses into clouds that stretch across continents. These clouds gather and release their moisture in patterns that follow the rhythm of seasons, the dance of atmospheric circulation, the patient work of a water cycle that mirrors Earth's but operates under alien parameters. Rain falls on virgin landscapes, droplets carrying dissolved minerals that will paint the chemistry of ancient seas. The water finds its way, as water always does, carving channels that begin as tentative scratches in the rock and grow into mighty valleys that will endure for eons. The first Martian rivers meander across plains that have never known the touch of flowing water, pooling in basins that become the first lakes under skies that reflect no previous memory of their own blue depths. This is fact, not speculation. We have seen the evidence written in stone across the planet's surface, inscribed in the very topography that greets our orbital cameras and rover wheels. The Curiosity rover has rolled through ancient streambeds in Gale Crater, its instruments detecting the chemical signatures of waters that flowed when our solar system was young. The Perseverance rover explores what was once the delta of a river system in Jezero Crater, reading the story of sustained water flow in every grain of sediment deposited across millions of years. These are not subtle hints that require creative interpretation. These are clear signatures of flowing water, persistent water, water that lasted long enough to carve landscapes and deposit sediments layer by careful layer. The evidence speaks in the language of fluvial geomorphology, in the vocabulary of river meanders and delta deposits, in the grammar of sedimentary sequences that record environmental change across geological time. The networks of valleys that spread across Mars's southern highlands tell stories of sustained precipitation that lasted not for seasons or years, but for millions of years. Not brief episodes that might result from catastrophic events, but climate systems that endured long enough to create mature drainage networks, river systems that had time to establish their courses, to carve their channels deeper with each flood season, to create the complex branching patterns we see preserved in the ancient terrain. River channels that meander and branch, just as rivers do on Earth when they have time to mature, time to find their way across stable landscapes. The sinuous curves speak of gentle gradients, of waters that moved with patient persistence rather than catastrophic violence. The tributary networks reveal watersheds that collected precipitation across vast areas, concentrating it into channels that carried the dissolved chemistry of continents toward ancient seas. In Jezero Crater, we see the fan-shaped delta, where a river once emptied into a lake that stretched across 40 kilometers of what is now dusty crater floor. The sediments tell us this was no fleeting puddle, but a body of water that persisted for millions of years, deep enough to stratify, stable enough to support complex chemistry, enduring enough to become a graveyard for whatever organic processes might have flourished in its waters, long enough for minerals to precipitate from solution, creating the carbonate platforms that ring ancient shorelines, long enough for organic molecules to concentrate in the shallows where sunlight could drive photochemistry, where temperature gradients could sort compounds by their molecular weight, where evaporation could concentrate the chemical soup that feeds complexity. Long enough, perhaps, for chemistry to explore possibilities we are only beginning to understand, pathways that lead from simple molecules to the intricate networks that characterize living systems. The minerals themselves preserve memories of this wetter world with the fidelity of geological archives. Clays that form only in the presence of liquid water, their crystal structures recording the temperature and pH of ancient solutions. Sulfates that crystallize from evaporating pools, their composition revealing the chemistry of waters that grew increasingly concentrated as climate began to change. Carbonates that speak of waters rich in dissolved carbon dioxide, of atmospheric interactions that created buffered chemical environments capable of sustaining delicate processes. Each mineral is a witness to conditions that existed for extended periods during Mars's youth, a testimony to environmental stability that provided the temporal foundation necessary for complexity to emerge. The clay minerals record gentle weathering processes that operated for millions of years. The sulfate deposits preserve evidence of gradual concentration as lake levels slowly declined. The carbonate formations capture the signatures of biological processes that might have modified water chemistry through metabolic activity. This period, which geologists call the Nokian era, lasted from Mars's formation until about 3.7 billion years ago. Nearly a billion years of time when water was not a rarity, but a defining feature of the Martian landscape, when the planet's surface hosted conditions that Earth would not achieve for hundreds of millions of years. A billion years is a vast span, longer than complex life has existed on Earth's surface, longer than photosynthesis has been altering our planet's atmospheric chemistry. During those long eons, Mars experienced cycles that we are only beginning to understand. Warm periods when the atmosphere was thickest, when greenhouse gases trapped heat and allowed water to flow freely across the surface, when volcanic outgassing replenished atmospheric losses, when impact events temporarily thickened the air with vaporized rock. Cooler periods when water retreated to underground reserves, when ice advanced and retreated across the changing climate zones, when the planet's orbital variations drove long-term cycles of environmental change. The magnetic field data from orbital magnetometers tells us that early Mars had a global magnetic field, generated by a molten core much like Earth's today, but perhaps even stronger, more complex in its structure. This magnetic shield protected the atmosphere from being stripped away by solar wind, creating a protective envelope that allowed atmospheric pressure to remain thick enough to support stable surface conditions, liquid water, and potentially the complex chemistry that leads to life. The paleomagnetic record preserved in ancient rocks reveals a dynamic magnetic field that underwent reversals and fluctuations, but maintained sufficient strength to deflect most of the solar wind's erosive effects. This protection was crucial during Mars's early evolution, when the sun was cooler but solar wind was more intense, when the planet's thick atmosphere and warm surface created conditions unprecedented in the modern solar system. Imagine standing on the shores of an ancient Martian lake during this remarkable period. The water laps gently against banks of layered rock, each stratum recording a chapter in the planet's climatic history. The air is thick enough to breathe, though alien in composition, rich with water vapor and carbon dioxide, perhaps tinged with sulfur compounds from distant volcanic regions. The pressure at the surface approaches that of Earth today, allowing liquid water to remain stable across a range of temperatures that spans the needs of complex chemistry. In the shallows, mineral grains settle slowly through the water column, beginning their transformation into the sedimentary records that will preserve this moment for billions of years. Organic molecules dissolved in the water undergo reactions driven by sunlight filtering through the thick atmosphere. Chemical gradients created by evaporation and mixing drive the formation of complex compounds that exist nowhere in the sterile chemistry of the modern Martian surface. The waves that disturb these ancient shorelines carry more than dissolved minerals. They transport organic compounds created in the complex chemistry of a young planet, where volcanic activity, atmospheric photochemistry, and hydrothermal systems create conditions favorable for the formation of the molecular building blocks of life. Each wavelength brings new combinations of elements, new possibilities for chemical complexity, new opportunities for the emergence of self-organizing systems. But this Mars of flowing water and thick atmosphere was not destined to last forever. The forces that created these remarkable conditions also contained the seeds of their own destruction. Slowly, over hundreds of millions of years, changes began that would transform the planet from a potential cradle of life into the frozen desert we know today. The magnetic field weakened as the core cooled, its protective strength diminishing as the planet's internal heat engine ran down. The protective envelope began to thin, allowing solar wind to begin its patient work of atmospheric erosion. Each solar storm stripped away a little more of the precious atmosphere. Each coronal mass ejection accelerated the loss of water vapor and other light gases to the vacuum of space. Solar wind started its patient work of stripping away the atmosphere molecule by molecule, preferentially removing the lighter elements that comprise the greenhouse gases necessary for maintaining warm surface conditions. Water vapor, hydrogen, helium, and light organic compounds were the first to go, bleeding away into space at rates that seem trivial on human timescales, but accumulate dramatically across geological ages. The volcanic activity that had replenished atmospheric gases began to decline as the planet's interior cooled. The massive shield volcanoes that dominate the Martian landscape today were built during this transition period. their eruptions representing the last gasps of a planet struggling to maintain the atmospheric chemistry necessary for surface habitability. As volcanic outgassing diminished, atmospheric losses to space began to exceed replenishment, initiating an irreversible decline toward the thin atmosphere of modern Mars. Yet even as the climate shifted toward the cold, dry world we know today, the memories remained, locked in stone with the permanence of geological time, preserved in the very landscape that our orbital cameras survey and our rovers explore, waiting for us to arrive with our robots and our questions, ready to read the story written in minerals and stone, patient as the planet itself in revealing its secrets to minds capable of understanding them. This is the Mars that was, a world of possibility, where the fundamental ingredients for complexity were not just present, but abundant, where time and stability allowed chemistry to explore pathways that might have led to something remarkable, something that might have left traces detectable by instruments sophisticated enough to read the subtle signatures preserved in ancient rocks. Let this image settle in your mind as you rest. A younger Mars under alien skies, where water carved its signature across landscapes that would endure for eons, carrying their secrets forward through deep time to the moment when curious minds from a neighboring world would finally arrive to read the story. Feel the patience of geological time, the persistence of evidence across unimaginable spans of years, the remarkable fact that information can survive the transformation of worlds. In this ancient Mars, we glimpse not just a different planet, but a different solar system, a time when multiple worlds might have harbored the conditions necessary for complexity to emerge. The water that once flowed on Mars connects us to possibilities that transcend our current understanding, reminding us that the cosmos is far richer and more remarkable than our Earth-centered perspective might suggest. Chapter 2. Memory in the Rock. Reading the past stone is memory, and within its layers lie the pages of a vanished climate. Rocks are the most patient storytellers in the solar system, archives that hold their secrets for billions of years, waiting for someone with the right eyes to read what they have preserved. On Mars, every crater rim, every exposed cliff face, every wind-carved outcrop is a library of the planet's history, written in a language that spans geological time and speaks of worlds that existed before our solar system settled into its current rhythms. The art of reading these stone archives begins with understanding how sediments form and persist, how the patient work of deposition creates layers that record not just the passage of time, but the environmental conditions that existed when each grain settled into place. When ancient Martian rivers carried their loads of sand and silt, they were creating more than just geological features. They were creating time capsules, preserving in mineral form the chemical signature of ancient atmospheres, the temperature records of vanished climates, the biological possibilities of a world in transition. Each grain of sediment tells a story of its journey from mountain slope to ocean floor, from volcanic ash cloud to river delta. The sharp-edged particles speak of short transport distances, of landscapes rapidly eroding under the influence of flowing water, of mechanical weathering that breaks rocks without the chemical alteration that comes with longer exposure to water and atmosphere. The well-rounded grains whisper of longer journeys, of patient rivers carrying their cargo across vast distances, tumbling and polishing the fragments until they became smooth testimony to persistent flow. The mineral composition of these sediments reveals the chemistry of the watersheds that produced them. Feldspar grains record the erosion of ancient igneous rocks. Quartz fragments speak of mature continental crusts. Clay minerals reveal the chemical weathering that occurs when water interacts with rock over extended periods. Each mineral assemblage provides clues about the climate, the water chemistry, and the geological processes that operated during deposition. When these sediments settle in the quiet waters of lakes and deltas, they arrange themselves in layers that follow principles as old as gravity itself. Larger, heavier particles settle first, creating beds rich in sand and gravel. Finer materials remain suspended longer, settling slowly to create the clay-rich layers that preserve the most delicate chemical signatures. Each layer represents a moment in time, a season, a flood, a drought, a volcanic eruption, a dust storm that blanketed the landscape in fine particles. The thickness of the layers reveals the intensity of deposition, the duration of events, the energy of the systems that transported and deposited the sediments. Thick layers speak of major floods, prolonged periods of intense erosion, catastrophic events that dramatically altered the landscape. Thin layers record gentle processes, the slow accumulation of materials during periods of environmental stability. The composition tells us about the chemistry of the ancient waters, the atmospheric conditions that influenced weathering, the biological processes that might have modified the chemical environment. Carbonate layers record periods when waters were rich in dissolved carbon dioxide. Sulfate deposits mark times when evaporation concentrated minerals in shrinking pools. Iron-rich layers preserve evidence of changing atmospheric chemistry, of oxygen levels that fluctuated with biological activity or volcanic outgassing. In Gale Crater, where the Curiosity rover has spent years exploring, we see this layered history exposed in remarkable detail in the central mountain called Mount Sharp. This towering formation rises 5 kilometers above the crater floor, its slopes displaying millions of years of Martian history in exposed rock faces that stretch for kilometers. Each stratum represents a different chapter in the crater's history, a different episode in the planet's environmental evolution. Lower layers speak of the lake that once filled this basin, their fine-grained structure recording the gentle deposition that occurs in deep, still waters. The presence of clay minerals reveals chemical conditions that could support complex organic chemistry. The absence of sulfates suggests fresh rather than saline waters, conditions more favorable for the emergence and persistence of life. Higher layers record the gradual drying, the transition from a water-rich environment to the arid landscape we see today. The appearance of sulfate minerals marks the period when the lake began to shrink and concentrate, when evaporation began to exceed precipitation, when the planet's climate system began its irreversible transition toward the harsh conditions of modern Mars. The rover's instruments can analyze these layers grain by grain, revealing the presence of minerals that form only under specific conditions, isotopic ratios that record ancient temperatures, organic compounds that might represent the preserved remains of ancient biological activity, hematite spherules, nicknamed blueberries, that precipitate from iron-rich waters, gypsum veins that crystallize as briny waters evaporate. Each discovery adds another sentence to the story of Mars's climatic history. The ChemCam laser spectrometer vaporizes tiny portions of rock from distances up to 7 meters, analyzing the elemental composition of the resulting plasma. This technique reveals not just what elements are present, but their concentrations, their associations with other elements, their distribution within individual mineral grains. The data builds a chemical map of Mars's ancient environment, with resolution measured in micrometers. But the most intriguing archives lie not in the exposed surfaces, but buried beneath the modern landscape, hidden beneath layers of dust and ice that have accumulated over millions of years. Ground-penetrating radar from orbiting spacecraft has revealed vast deposits of layered sediments hidden beneath the polar ice caps, beneath the dust sheets that cover much of the planet's surface, beneath volcanic deposits that erupted long after the ancient climate systems collapsed. These subsurface layers represent the most complete records of Mars's climate history, archives that escape the erosion and modification that have affected surface exposures. Like tree rings, they preserve annual cycles, capturing the subtle changes in atmospheric composition, dust deposition, and seasonal patterns that played out over millions of years. Each layer, sometimes just millimeters thick, represents a year in Mars's deep past, a complete record of the atmospheric conditions that existed during that particular orbit around the Sun. The North Polar deposits contain layers that extend back at least 3.7 billion years, creating a climate record more complete and extensive than any other archive in the solar system. Together, they form a book with millions of pages, each page recording the state of the planet's atmosphere and climate system during a specific year in the distant past. This archive preserves evidence of climate oscillations driven by changes in orbital parameters, volcanic events that altered atmospheric chemistry, impact events that temporarily thickened the atmosphere. In these polar archives, we find evidence of dramatic climate oscillations that occurred on timescales ranging from years to millions of years. Periods when the atmosphere was thicker, when dust storms were less frequent, when the polar ice caps advanced and retreated in response to changes in the planet's orbital cycles. The layers preserve evidence of volcanic epochs when ash and sulfur compounds altered atmospheric chemistry for centuries or millennia. They record impact events that temporarily thickened the atmosphere with vaporized rock, creating brief greenhouse episodes that might have restored liquid water to the surface for thousands of years. They preserve the signatures of solar variations, magnetic field changes, and other factors that influenced Mars's climate across geological time. Deltas and lakebeds represent another crucial type of archive, depositional environments that concentrate organic molecules and preserve them in fine-grained sediments that exclude oxygen and prevent decay. On Earth, similar environments have preserved fossils spanning billions of years, including some of our earliest evidence for microbial life, the chemical signatures of ancient biological processes, the isotopic ratios that reveal how life has influenced planetary chemistry. The delta in Jezero crater is perhaps the most promising archive we have yet identified on Mars, a formation that represents millions of years of deposition in an environment ideally suited for preserving evidence of ancient life. Here, a river system deposited sediments for millions of years, creating ideal conditions for preservation of organic materials, biological structures, chemical signatures that might reveal whether life ever emerged in Mars's ancient waters. The fine clays at the delta front would have been perfect for trapping and preserving any organic molecules present in the ancient waters. The reducing environment that develops in such sediments protects organic materials from oxidation and decay. The rapid burial by overlying sediments creates conditions that can preserve even delicate biological structures for billions of years. Each sample that the Perseverance rover collects from this delta is like opening a time capsule from Mars's distant past, a window into environmental conditions that existed when our solar system was young and Mars was a very different world. The organic molecules we have already detected may represent the preserved remains of ancient biological processes, or they may be the products of purely geological chemistry. Either discovery would be profound. Either would reshape our understanding of Mars's potential for complexity. The patience required to read these archives matches the patience with which they were created. Years of careful analysis are required to extract meaningful information from each sample, to distinguish biological signatures from geological processes, to understand the environmental conditions that existed during deposition. But the rewards are immense. each new piece of data adding depth to our understanding of how planets evolve, how climates change, how life might emerge and persist in environments very different from modern Earth. Advanced analytical techniques continue to reveal new information from samples collected years or even decades ago. Improvements in mass spectrometry allow detection of organic compounds at concentrations measured in parts per trillion. Enhanced imaging techniques reveal microscopic structures that might represent preserved cellular materials. Isotopic analysis provides increasingly precise information about ancient temperatures, atmospheric compositions, and biological processes. As you rest tonight, consider the remarkable fact that memories can be preserved in stone for billions of years, that information about ancient worlds survives the transformation of planets, the evolution of solar systems, the vast changes that occur across cosmic time. The rocks of Mars carry within them the echo of ancient rains, the chemistry of vanished lakes, the signature of atmospheric compositions that existed when our solar system was young and full of possibilities we are only beginning to understand. Every mission to Mars is an archaeological expedition, carefully excavating not artifacts, but moments in time preserved in mineral form. We are learning to read the language written in crystal lattices, to decode the stories told by isotopic ratios, to understand the narratives preserved in the very structure of ancient sediments. Layer by layer, sample by sample, we are reconstructing a world that existed so long ago that its light has been traveling toward us since before complex life emerged on Earth. In these patient stones, we find not just the history of Mars, but clues to the history of planetary evolution itself, evidence of the processes that shape worlds and create the conditions where complexity can emerge. The rocks remember what the sky has forgotten. They hold their secrets close, waiting for minds curious enough to ask the right questions, careful enough to listen to whispers preserved across the vast expanses of deep time. In learning to read these stone archives, we develop new capacities for understanding time itself, for recognizing the persistence of information across scales that dwarf human experience. Chapter 3. From life to complexity, where water and energy meet, the spark of life may flicker, sometimes faint, sometimes enduring. Life is both remarkably fragile and astonishingly persistent. On Earth, we find living organisms in environments that would have seemed impossible just decades ago. In the crushing depths of ocean trenches, in the acidic hot springs of volcanic regions, in the frozen Antarctica valleys where liquid water has not flowed for millions of years, life finds a way to persist, to adapt, to colonize even the most challenging environments. The question that draws us to Mars is whether life ever found a way there as well. We must begin with what life requires, at its most fundamental level. Life, as we understand, it needs liquid water as a solvent for the chemical reactions that drive biological processes. It needs sources of energy, whether from sunlight, chemical gradients, or radioactive decay. It needs the basic elements that form the molecules of life: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Ancient Mars had all of these ingredients in abundance. The water was there, flowing in rivers, pooling in lakes, percolating through underground aquifers. The energy was there, from a younger, more active sun, from the planet's own internal heat, from the chemical potential locked in minerals exposed to the atmosphere and hydrosphere. The organic chemistry was there. We know this not from speculation, but from direct measurement. The Curiosity rover has detected complex organic molecules preserved in 3.5 billion-year-old rocks. Molecules containing carbon-sulfur bonds, carbon-nitrogen bonds, aromatic ring structures. These are not simple compounds, but the kinds of complex organic chemistry that on Earth serves as the foundation for biological processes. Some of these organic molecules might be the remnants of ancient biological activity. Others might be the products of purely geological processes, the result of interactions between water, minerals, and the organic compounds delivered by meteorites and comets. Both possibilities are fascinating. If these molecules represent ancient biology, they would be the first direct evidence of life beyond Earth. If they represent geological chemistry, they demonstrate that the raw materials for life can form spontaneously under Martian conditions. But life requires more than just the right ingredients. It requires time and stability for those ingredients to organize themselves into self-replicating systems. Early Mars provided both. The Nokian era lasted nearly 1 billion years. That is time enough for chemistry to explore countless possibilities, for random processes to stumble upon combinations that could persist and reproduce. On Earth, the earliest evidence for life appears in rocks about 3.7 billion years old, formed when our planet was roughly the same age that Mars was when its climate began to change. The environments where early life might have emerged on Mars were diverse. Hydrothermal systems around volcanic areas could have provided concentrated sources of chemical energy. River deltas would have created interfaces between different chemical environments. Underground aquifers could have offered stable conditions protected from surface variations. Consider the subsurface environments in particular. Even as Mars's surface climate grew hostile, vast volumes of liquid water likely persisted underground. Protected from radiation and temperature extremes, these subsurface ecosystems could have provided refuge for life that first emerged during the planet's more hospitable early period. On Earth, we are only beginning to understand the extent and importance of the subsurface biosphere. Microorganisms living kilometers beneath the surface derive energy from chemical reactions between water and rock. They reproduce slowly, sometimes taking centuries to complete a single generation, but they persist in environments that have remained stable for millions of years. If similar organisms emerged in Mars's subsurface, they might persist there still, living in the deep aquifers that likely exist beneath the frozen surface. This possibility drives much of our current search for life on Mars. We look not only for evidence of ancient life, but for signs that biological processes might continue in the planet's hidden depths. The isotopic signatures we measure in Martian meteorites provide tantalizing hints about biological possibilities. The ratios of carbon isotopes, sulfur isotopes, and nitrogen isotopes show patterns that on Earth would suggest biological processing. These signatures are subtle, open to multiple interpretations, but they suggest that the chemistry of ancient Mars was complex and dynamic. Methane detected in the modern Martian atmosphere adds another piece to this puzzle. Methane is a molecule that breaks down quickly under Martian conditions, so its presence suggests active sources. On Earth, most atmospheric methane is produced by biological processes, though geological sources also exist. The methane on Mars appears seasonally and regionally, suggesting localized sources that remain mysterious. But even if life did emerge on ancient Mars, would it have remained simple, or could it have evolved toward greater complexity? The answer depends on stability, energy availability, and time. Earth's transition from simple microbial life to complex multicellular organisms required nearly 3 billion years and was driven by specific environmental changes, particularly the rise of atmospheric oxygen. Mars's climate became increasingly harsh much earlier in its history, potentially truncating such evolutionary developments. Yet for hundreds of millions of years, Mars maintained environments that could have supported not just simple life, but potentially complex microbial communities. We see analogous communities on Earth in environments like Yellowstone's hot springs, where diverse microorganisms create layered mats, establish symbiotic relationships, and process chemicals in ways that modify their local environment. Such microbial complexity could have emerged on Mars during its most hospitable periods. These communities might have created their own chemical signatures, altered the composition of local waters, even modified atmospheric chemistry through their metabolic processes. The transition from habitability to actual biology remains one of the deepest mysteries in science. We understand the conditions that life requires, but we do not yet understand the specific pathways by which chemistry becomes biology. Mars provides a natural laboratory for exploring this transition, offering examples of environments where the necessary conditions existed for extended periods. As you drift towards sleep tonight, consider this remarkable possibility that life may have emerged independently on two worlds in our solar system, finding different pathways to complexity under different environmental constraints. Whether that life persisted, evolved, or vanished, its study offers profound insights into the nature of life itself. The search for life on Mars is ultimately the search for answers to some of our deepest questions. Are we alone? How does life begin? What are the limits of biological adaptation? In the rocks and sediments of our neighboring world, we may find answers that reshape our understanding of life's possibilities throughout the universe. Chapter 4: Civilization. Definitions and scales. When we speak of civilization, we speak of traces, structures, order, energy sustained marks that cross time. The word civilization carries weight, implies complexity, suggests achievements that transcend basic survival and venture into the realm of conscious design, deliberate modification of environment, and the transmission of knowledge across generations. But what exactly do we mean when we ask whether Mars might once have harbored civilization? To explore this question responsibly, we must first define our terms with care, examining what distinguishes civilization from mere life, what separates conscious design from biological adaptation, what makes the difference between individual intelligence and collective achievement. Civilization, at its most basic level, involves the organized manipulation of environment and resources beyond what individual organisms require for immediate survival. It implies sustained cooperation between individuals, the ability to share information across generations, and the capacity to modify environments in ways that persist beyond individual lifespans. It suggests the emergence of collective intelligence, systems of knowledge that transcend what any single mind can contain, technologies that amplify the capabilities of individual organisms beyond their biological limitations. By these broad criteria, even some Earth species achieve rudimentary forms of civilization. Beaver dams alter entire watersheds for generations, creating artificial lakes that persist long after the original builders have died, establishing ecological conditions that support complex communities of organisms that would otherwise be unable to survive in those environments. These structures represent conscious design, deliberate modification of natural systems to achieve specific goals, the application of inherited knowledge to solve environmental challenges. Coral reefs create complex three-dimensional structures that persist for millennia, providing habitat for thousands of species while actively modifying water chemistry, ocean circulation patterns, and coastal geology. These biological cities represent cooperative achievement on a vast scale, collective construction projects that require coordination between countless individual organisms, working toward common goals across extended periods of time. Social insects build sophisticated colonies with specialized castes, engineered environments, and complex communication systems that coordinate the activities of millions of individuals. Ant colonies create underground cities with ventilation systems, waste management infrastructure, and agricultural facilities that sustain populations far larger than the carrying capacity of the natural environment would allow. These examples demonstrate that civilization, in its broadest sense, represents an extension of biological capabilities through collective action, environmental modification, and information transmission. The boundary between biology and technology is not as sharp as we might assume, with many organisms using tools, modifying their environments, and creating structures that persist across generations. But when we speak of the possibility of ancient Martian civilization, we typically envision something more sophisticated than these biological examples. We imagine technological capability, the ability to harness energy sources beyond metabolism, the creation of artifacts that could survive geological time, the development of systems of knowledge that transcend biological inheritance. We think of civilization as the emergence of culture, the development of symbolic communication, the creation of abstract knowledge that can be preserved and transmitted independently of genetic inheritance. This is where careful thinking becomes essential, where we must balance our natural desire to find signs of intelligence with rigorous analysis of what such signs might actually look like. The vast majority of civilizations that might emerge on any world would likely leave little trace after millions or billions of years of geological processing. The forces that preserve some types of evidence also destroy others, creating a selective bias towards certain kinds of signatures while eliminating others completely. Consider the challenges of preservation across geological time. Organic materials decay within centuries or millennia under most environmental conditions. Most metals oxidize within decades without maintenance, their original forms lost to corrosion and chemical alteration. Even our most durable artifacts, objects made of stone and ceramic, show clear signs of erosion after just thousands of years of exposure to weathering processes. Now, consider the time scales involved in Martian history. The most recent period when the planet's climate might have supported complex surface activity was over 3 billion years ago, a span of time that challenges our ability to comprehend its enormity. 3 billion years is long enough for mountain ranges to rise and erode away completely, for continents to shift their positions, for the entire surface of a planet to be recycled through geological processes multiple times. On Earth, we can detect the signatures of ancient microbial life in rocks that are 3.5 billion years old, but these represent chemical fossils rather than physical structures, molecular traces preserved under very specific conditions rather than artifacts in any conventional sense. The oldest evidence for complex multicellular life dates back only about 600 million years, and the preservation of these fossils required exceptional circumstances that occur rarely in the geological record. Any civilization that might have existed during Mars's early, more hospitable period would have faced this inexorable erosion of evidence. Only the most durable artifacts, or those protected in very special circumstances, would have any chance of surviving to the present day. The signatures we seek must be robust enough to persist across time scales that dwarf anything in human experience, subtle enough to escape detection by earlier, less sophisticated surveys, yet distinctive enough to distinguish them from natural phenomena. What kinds of traces might endure across such vast time spans? The answer requires us to think beyond conventional archaeology, to imagine signatures that transcend the materials and structures that characterize human civilization. We must consider modifications that operate at geological scales, changes that become integrated into the planetary system itself, alterations that persist because they have become part of the fundamental structure of the world. Geometric anomalies in geological formations, might represent the most durable signatures of ancient intelligence. If an ancient civilization had the ability to move large quantities of rock or earth, the patterns they created might remain visible even after billions of years of erosion. The geometric relationships would persist even as the original structures weathered away, leaving behind statistical signatures that could be detected through careful analysis of topographic data. Regular spacing of features across vast landscapes might indicate artificial origin, particularly if the spacing follows mathematical relationships rather than the power law distributions that characterize most natural phenomena. Alignments that follow astronomical orientations rather than geological trends could suggest deliberate design. Artificial channeling of water flow might create drainage patterns that differ subtly but significantly from naturally evolving river networks. The challenge lies in distinguishing these artificial signatures from the remarkable geometric patterns that natural processes can create. Basalt columns form hexagonal patterns through purely physical processes. Sand dunes create regular spacing through wind interactions. River networks develop fractal branching patterns that follow mathematical laws. The key is identifying patterns that show characteristics inconsistent with known natural processes, anomalies that require intelligence to explain. Chemical signatures might prove more persistent than physical structures, representing modifications to planetary chemistry that become integrated into geological cycles. Industrial processes, large-scale mining operations, or the concentration of rare elements in unusual locations could create geochemical anomalies that would remain detectable long after the civilization that created them had vanished. On Earth, we can detect the signatures of ancient biological activity in chemical patterns that persist for billions of years. The isotopic ratios of carbon, sulfur, and nitrogen in ancient rocks preserve evidence of metabolic processes that operated when our planet was young. Similar chemical fossils might preserve evidence of technological processes that operated on ancient Mars. Large-scale mining operations would leave distinctive signatures in the distribution of elements across planetary surfaces. Natural ore deposits follow patterns determined by geological processes. Hydrothermal systems, sedimentary concentration, igneous differentiation, artificial extraction, and redistribution would create patterns that violate these geological expectations, concentrating rare elements in locations where natural processes would not place them. Isotopic ratios offer another possible signature of technological activity. Industrial processes often fractionate isotopes in ways that differ from natural geological processes, creating distinctive signatures that can persist for billions of years. Nuclear technology, in particular, would create isotopic anomalies that would remain detectable across geological time, though detecting such signatures would require very sophisticated analytical techniques applied to carefully selected samples. The challenge lies in distinguishing artificial isotopic signatures from the natural variations that result from geological processes, biological activity, and cosmic ray interactions. Each type of process creates distinctive patterns, but interpreting these patterns requires detailed understanding of all the natural processes that might have operated on ancient Mars. Subsurface modifications might offer the best chance of preservation across geological time. Underground chambers, artificial cave systems, or deep excavations could potentially survive surface erosion while preserving clear evidence of artificial origin. The stable underground environment might protect not only the structures themselves, but also artifacts contained within them, creating time capsules that preserve evidence of ancient intelligence. Natural cave systems exist throughout Mars, carved by flowing water, volcanic activity, and other geological processes. Artificial modifications to these natural spaces might be detectable through geometric analysis, showing patterns of enlargement, reinforcement, or interconnection that differ from natural cave development. The presence of artificial materials, geometric regularity, or evidence of tool use could distinguish modified caves from purely natural formations. Deep excavations, if they existed, might remain detectable through geophysical surveys that reveal subsurface voids, artificial chambers, or modifications to natural geological structures. The geometric characteristics of such excavations would likely differ from natural cavities, showing evidence of deliberate design rather than the irregular patterns created by natural processes. But we must also consider alternative forms that ancient Martian complexity might have taken, possibilities that challenge our anthropocentric assumptions about what civilization must look like. Perhaps evolution on Mars followed different pathways than on Earth, creating forms of intelligence that emphasize different capabilities, develop different relationships with their environment, pursue different strategies for survival and growth. Perhaps biological sophistication developed without technological infrastructure, creating living systems that achieved complexity through biological rather than mechanical means. Imagine organisms that could modify their environment through biological processes, creating living cities that grew rather than being built, developing collective intelligence through biological communication networks rather than technological systems. Such biological civilizations might leave very different signatures than technological ones. Chemical modifications to environmental systems, biological structures that persist as fossils, genetic modifications that remain detectable in the genomes of descendant organisms, living systems that become integrated into planetary ecology in ways that persist across geological time. Consider also the possibility of subsurface civilization, intelligence that retreated underground as surface conditions became hostile. If surface conditions became uninhabitable early in Mars's history, intelligent life might have adapted to subsurface environments, developing technologies specifically designed for underground existence rather than surface activity. Underground civilizations might persist for millions or even billions of years in the stable conditions beneath the surface, sustained by geothermal energy and protected from surface catastrophes. They might develop along entirely different lines than surface-based intelligence, emphasizing capabilities we have never considered, pursuing goals we cannot imagine, creating signatures we are not equipped to detect. The time scales of Martian geological history also suggest different developmental pathways might have been possible. On Earth, complex life required nearly 4 billion years to develop technological capability, but this timeline was shaped by specific evolutionary pressures and environmental constraints. Different environments might favor different types of complexity, different rates of development, different relationships between intelligence and technology. Mars's early environment, with its thinner atmosphere, different chemistry, and unique geological processes, might have favored the evolution of organisms with capabilities we have never seen on Earth. Perhaps intelligence developed along pathways that emphasized chemical rather than physical manipulation of environment. Perhaps complexity emerged that was more integrated with geological processes than anything we can easily recognize. The reduced gravity on Mars might have enabled biological architectures impossible on Earth, organisms that could grow to enormous sizes, structures that could span vast distances without the engineering challenges that limit terrestrial organisms. The different atmospheric composition might have enabled biological processes that cannot operate in Earth's environment, metabolic pathways that create byproducts we would not recognize as biological. The unique geological environment of early Mars, with its extensive volcanic activity, hydrothermal systems, and complex water chemistry, might have created opportunities for biological and technological development that have no parallels in Earth's history. Intelligence might have emerged that was specifically adapted to these unique conditions, developing capabilities that would seem remarkable from our perspective, but represented natural adaptations to Martian environmental challenges. The search for signs of ancient Martian civilization thus becomes a search for anomalies, for patterns that don't fit our understanding of purely geological processes, for signatures that suggest deliberate modification of natural systems. It requires instruments sensitive enough to detect subtle chemical signatures, imaging systems capable of resolving geometric patterns across vast landscapes, analytical techniques sophisticated enough to distinguish artificial modifications from natural variations. Most importantly, it requires intellectual humility and openness to possibilities that challenge our assumptions about what intelligence must look like, how it must develop, what signatures it must leave. We must remain open to the possibility that complexity might have emerged in forms very different from our own experience, leaving traces that require new methods of detection, new frameworks of interpretation, new approaches to understanding the relationship between intelligence and environment. The signatures we seek might be subtle, requiring years or decades of careful analysis to confirm. They might be ambiguous, open to multiple interpretations, challenging our assumptions about the boundary between natural and artificial processes. They might be integrated into planetary systems in ways that make them difficult to distinguish from natural phenomena without sophisticated analytical techniques. As you settle into rest, consider this. The search for ancient Martian civilization is ultimately a search for our own cosmic context, an exploration of whether intelligence represents a rare accident or a natural outcome when the right conditions persist for sufficient time. If intelligence has emerged more than once in our solar system, it suggests that the universe might be rich with thinking beings, that consciousness might be a common property of matter organized under appropriate conditions. If we find that we are alone even in our local neighborhood, it emphasizes the precious rarity of consciousness and the remarkable chain of circumstances that led to its emergence on Earth. It highlights our responsibility as possibly the only current thinking beings in our region of space, the unique burden and privilege of consciousness in a universe that might be largely unconscious. Either answer would profoundly shape our understanding of our place in the universe, our responsibilities as conscious beings, our approach to exploring and protecting the environments that might harbor intelligence. The red planet holds clues to these deepest questions, waiting patiently for us to develop the tools and wisdom necessary to read the signs preserved in its ancient rocks. Chapter 5. Traces that might remain if someone once lived there. What would remain? Perhaps small traces, whispers barely remembered by the planet. Time is the great eraser, particularly on a world where dust storms can engulf entire continents and erosion operates with patient inevitability across billions of years. Yet even time has limits, boundaries beyond which some signatures resist destruction. Some patterns endure against all odds. Some anomalies survive to tell their stories to those who know how to look and have developed the wisdom to interpret what they find. If ancient Mars harbored intelligence, what traces might we find today? The question requires us to think beyond the conventional artifacts that characterize human archaeology, to imagine signatures that operate at planetary scales, modifications that become integrated into geological systems, changes that persist because they have fundamentally altered the structure of the world itself. The most obvious signatures would be geometric, impositions of order upon the random processes of nature that reveal the hand of intelligence through mathematical precision, statistical regularity, and purposeful design. Intelligence imposes order on chaos, creates patterns that stand out against the random distributions that characterize natural phenomena, establishes relationships that follow conscious design, rather than the power laws and fractal patterns generated by physical processes. On Earth, even our most ancient human settlements leave geometric traces visible from orbit, despite thousands of years of abandonment and natural reclamation. Stone circles that maintain their proportions across millennia. Linear earthworks that stretch across landscapes in straight lines that never occur in natural drainage systems. Regular spacing of settlements along rivers and coastlines that follows economic logic rather than purely geographical constraints. The Roman road system remains visible in aerial photography after 2,000 years, its geometric precision distinguishing it from the meandering paths created by natural erosion or animal migration. Ancient field systems create regular patterns that persist in soil chemistry and topography long after the boundaries themselves have vanished. Harbor installations modify coastlines in ways that remain detectable millennia after the civilizations that built them have disappeared. Martian geometric anomalies might take different forms, adapted to the planet's unique environment and the capabilities of whatever intelligence might have emerged there. The signatures might be subtle, requiring statistical analysis to distinguish them from natural phenomena, or they might be dramatic, creating patterns so regular that they could only result from conscious design. Regular spacing of crater modifications might indicate artificial origin, particularly if the spacing follows mathematical relationships rather than the geological processes that typically determine crater distribution. Natural crater formation follows random patterns determined by the statistics of asteroid impacts. Artificial modifications would create regularities that violate these statistical expectations. Linear arrangements of geological features could suggest deliberate modification of natural landscapes. River channels that have been artificially straightened maintain geometric characteristics that differ from naturally meandering systems. Artificial terracing creates geometric patterns that reflect engineering principles rather than natural erosion processes. Geometric patterns in sediment deposits might preserve evidence of ancient construction activities. Large-scale earth-moving operations would create artificial landforms that influence drainage patterns, sediment deposition, and erosion for millions of years after the original construction. These signatures might be detectable through careful analysis of sedimentary sequences and topographic data. Artificial channeling of ancient water flows could create drainage networks that differ subtly but significantly from natural river systems. Natural drainage follows predictable patterns determined by topography, geology, and climate. Artificial modifications create geometric regularities, water flow patterns that follow engineering principles rather than purely natural processes. The famous face on Mars in the Cydonia region captured public imagination precisely because it seemed to show geometric regularity, artificial symmetry that suggested conscious design. Higher resolution imaging revealed it to be a natural formation, but the initial reaction was understandable and scientifically appropriate. Our pattern-seeking minds are correctly attuned to detect signs of intelligence, even where none exist. This phenomenon, called pareidolia, reminds us that we must be careful in our search for artificial patterns while remaining open to genuine discoveries. The human mind excels at finding meaningful shapes in random configurations. Clouds that look like animals, rocks that resemble faces, geological formations that suggest artificial construction are all products of our evolved tendency to seek patterns and meaning in natural phenomena. Yet genuine artificial patterns do have characteristics that distinguish them from random formations when subjected to rigorous analysis. True geometric regularity that extends across multiple scales. Precise mathematical relationships that cannot be explained by known natural processes. Orientations that align with astronomical phenomena rather than prevailing winds or geological structures. If we found a series of circular formations, each exactly 100 meters in diameter, arranged in a perfect hexagonal grid across a Martian plain, aligned with the planet's magnetic field rather than its topography, we would have strong evidence for artificial origin. Such patterns would be extraordinarily unlikely to arise through natural processes, representing statistical signatures that demand explanation through conscious design. The challenge lies in developing analytical techniques sophisticated enough to detect these statistical anomalies, while avoiding the trap of seeing intelligence where none exists. Machine learning algorithms trained on vast databases of natural phenomena can identify patterns that fall outside the expected range of natural variation. Statistical analysis can quantify the probability that observed patterns result from random processes. Chemical anomalies might provide more reliable signatures than geometric patterns, representing modifications to planetary chemistry that persist long after the physical structures that created them have vanished. Industrial processes concentrate elements in ways that differ fundamentally from natural geological processes, creating chemical fingerprints that can survive geological recycling. Large-scale manufacturing creates chemical byproducts that persist in soils and sediments for millions of years. Mining operations leave distinctive signatures in the distribution of metals and minerals that can be detected through sophisticated geochemical analysis. Industrial processes create artificial concentrations of elements that would be dispersed much more evenly by natural processes. On Earth, we can detect the signatures of ancient human metallurgy in ice cores dating back thousands of years, chemical evidence of activities that occurred long before written history. Lead pollution from Roman silver mines appears in Greenland ice layers deposited 2,000 years ago. Copper smelting operations leave traces in lake sediments across Europe, chemical fossils of technological activity that persist long after the civilizations that created them have vanished. These signatures persist because they represent artificial concentrations of elements that violate the patterns created by natural geochemical cycles. Natural processes tend to disperse elements according to their chemical properties and the physical processes that transport them. Artificial concentration creates patterns that stand out against this natural background. Martian chemical anomalies might take forms that reflect the unique conditions and materials available on that world. Unusual concentrations of rare earth elements in sediment layers that cannot be explained by known geological processes. Artificial isotope ratios that differ from the patterns created by natural nuclear processes. Organic compounds that exist in combinations never seen in purely geological contexts. The organic molecules already detected in Martian rocks by our most sophisticated analytical instruments show levels of complexity that raise intriguing questions about their origin. Some of these molecules form naturally through interactions between water, minerals, and organic compounds delivered by meteorites, but others represent molecular architectures that are difficult to explain through purely geological processes. Biological processes create organic molecules with specific handedness, a form of molecular asymmetry that reflects the biochemical processes that produce them. Finding such asymmetries in Martian organics could indicate biological origin, evidence that living systems once operated on the red planet. If we discovered organic compounds with the opposite-handedness from Earth biology, it might suggest an independent origin of life, a separate evolutionary pathway that made different fundamental choices about molecular architecture. The preservation of these chemical signatures depends on environmental conditions that protect organic molecules from degradation over geological time. The cold, dry conditions that characterize modern Mars actually favor preservation of organic materials, creating natural archives that might preserve chemical evidence of ancient biological or technological activity for billions of years. Energy signatures offer another possible trace of ancient intelligence, modifications to natural energy flows that create detectable anomalies in thermal, electromagnetic, or gravitational fields. Large-scale energy use leaves distinctive patterns that can persist long after the technology that created them has vanished. Heat anomalies from concentrated energy production might remain detectable through infrared surveys. Artificial modification of natural energy flows could create signatures that distinguish them from purely geological phenomena. Modern Mars shows intriguing thermal anomalies in some regions, localized warm spots that don't correlate with known geological activity, such as volcanic systems or hydrothermal features. These could represent natural processes that we don't yet understand: subsurface water reservoirs, chemical reactions between water and rock, or residual heat from impact events. But they could also indicate ongoing energy production from artificial sources. The interpretation of these thermal anomalies requires careful analysis that considers all possible natural explanations before invoking artificial origins. Geothermal systems can create localized heat sources that persist for millions of years. Chemical weathering processes can generate heat through oxidation reactions. Radioactive decay in concentrated mineral deposits can create thermal signatures that appear anomalous without sophisticated geochemical analysis. Underground modifications might provide the most durable signatures of ancient intelligence, creating structural changes that survive surface erosion while preserving clear evidence of artificial origin. Excavated chambers, artificial cave systems, underground water management systems, and deep mining operations could all potentially survive the surface weathering that has obscured most traces of Mars's ancient past. Ground-penetrating radar from orbital platforms has revealed complex subsurface structures across Mars, three-dimensional maps of buried layers, cavities, and formations that provide unprecedented views of the planet's hidden architecture. Most of these features represent natural geological phenomena: lava tubes carved by flowing molten rock, sediment layers deposited by ancient water systems, buried impact craters preserved beneath newer formations. But some anomalies remain unexplained, showing geometric regularity or structural complexity that doesn't fit obvious geological explanations. Subsurface chambers with artificial symmetry, tunnel systems that connect natural caves in patterns that suggest deliberate engineering, underground voids that show evidence of excavation rather than natural formation. The challenge lies in distinguishing artificial modifications from the remarkable range of structures that natural processes can create. Volcanic activity produces complex underground chambers and tunnel systems. Water erosion carves intricate cave networks. Tectonic processes create underground fractures and voids that can show surprising regularity. The key is identifying characteristics that are inconsistent with known natural processes, geometric precision that exceeds what natural forces can achieve, structural relationships that suggest conscious design, modifications to natural features that serve recognizable purposes. These signatures might be subtle, requiring sophisticated analysis to distinguish them from natural phenomena. The polar layered deposits contain millions of years of accumulated sediments, creating the most complete climate record available anywhere in the solar system. Within these layers, we might find evidence of artificial climate modification, atmospheric engineering, or large-scale environmental projects that altered the planet's atmospheric composition during ancient periods. Dust layers in the polar deposits could preserve signatures of massive construction projects, industrial activities, or environmental catastrophes that created distinctive chemical signatures in the atmospheric record. On Earth, volcanic eruptions create distinctive layers in ice cores that can be detected thousands of years later. Nuclear weapons testing has left radioactive markers in sediments worldwide. Similar signatures might exist in Martian polar ice, recording the activities of ancient civilizations in the planet's atmospheric archive. The analysis of these polar records requires techniques borrowed from paleoclimatology, atmospheric chemistry, and environmental science. Each layer represents a snapshot of atmospheric conditions during a specific year in Mars's history. Chemical analysis can reveal the presence of artificial compounds, unusual isotopic ratios, or elemental concentrations that suggest technological activity. Biological modifications present another category of possible traces, signatures that reflect the activities of intelligence working through biological rather than purely technological means. If intelligence emerged on Mars, it might have modified local ecosystems, created artificial organisms, or left behind biological signatures in the form of preserved genetic material that could survive in frozen environments for millions of years. Recent discoveries of DNA preservation in extreme environments on Earth suggest that genetic material might survive much longer than previously thought possible under appropriate conditions. In permanently frozen environments, protected from radiation and chemical degradation, DNA can potentially remain intact for millions of years, preserving information about the organisms that created it. Martian permafrost might preserve biological materials from the planet's earlier, more hospitable periods, creating natural freezers that maintain organic molecules in stable conditions across geological time. If intelligence emerged during these periods, it might have left biological traces preserved in the deep frozen soil layers that blanket much of the planet's surface. The search for these biological signatures requires techniques borrowed from molecular biology, genetics, and astrobiology. DNA sequencing technology might be able to identify preserved genetic material in carefully collected samples. Protein analysis could reveal the presence of biological molecules that don't occur in purely geological contexts. Metabolic markers could indicate ancient biological activity. Artificial structures adapted to Martian conditions might take forms we haven't considered, architectures that work with the planet's unique environment rather than against it. Perhaps subsurface civilizations developed building techniques based on excavation and reinforcement rather than construction and assembly. Perhaps they learned to work with Mars's unique geology, creating structures that blend seamlessly with natural formations while serving artificial purposes. Consider the possibility of biological architecture, structures grown rather than built through genetic engineering of organisms specifically adapted to Martian conditions. Intelligence might have modified organisms to create living buildings, transportation systems, or manufacturing facilities that could survive and function in the harsh environment, while leaving biological rather than technological signatures. Such biological technology would leave very different traces than mechanical systems, but might be better adapted to Mars's environmental challenges. Living systems can self-repair, adapt to changing conditions, and evolve in response to environmental pressures in ways that mechanical technology cannot. Biological signatures might persist in genetic material, metabolic products, or structural modifications to natural ecosystems. The search for these traces requires patience, sophisticated instrumentation, and careful analysis that considers all possible natural explanations before invoking artificial origins. Distinguishing artificial signatures from natural anomalies demands detailed understanding of Mars's geological processes, atmospheric chemistry, and biological possibilities. Each type of potential signature requires different analytical techniques, different types of evidence, different levels of proof. Chemical anomalies might be detectable through spectroscopic analysis of surface materials. Geometric patterns require statistical analysis of topographic and imaging data. Subsurface modifications need geophysical surveys and ground-penetrating radar. Biological signatures demand molecular analysis of carefully preserved samples. The integration of multiple types of evidence provides the strongest foundation for claims about artificial origin. Single anomalies can almost always be explained through natural processes, but when multiple independent lines of evidence converge on the same locations, when geometric patterns coincide with chemical anomalies and subsurface structures, the case for artificial origin becomes increasingly compelling. As you rest tonight, imagine the patient work of detection unfolding across decades and centuries of careful exploration. Each new mission to Mars carries instruments more sensitive than the last, capable of detecting subtler anomalies, analyzing smaller samples, resolving finer details in the planet's complex structure and composition. Perhaps tomorrow's discoveries will reveal clear evidence of artificial patterns, chemical signatures that can't be explained by geology alone, structures that bear the unmistakable hallmarks of intelligence and conscious design. Or perhaps we will find that Mars's anomalies all have natural explanations, that intelligence never emerged on our neighboring world, that we remain alone in our local corner of the solar system. Either answer would be profound, reshaping our understanding of intelligence, consciousness, and our place in the cosmic order. Evidence of ancient Martian intelligence would revolutionize our understanding of life's possibilities in the universe, demonstrating that consciousness can emerge under conditions very different from those that characterized Earth's history. Evidence of Mars's sterility would emphasize the preciousness of consciousness and the remarkable chain of circumstances that led to its emergence on Earth, highlighting our responsibility as possibly the only thinking beings in our local region of space. The traces we seek are whispers from deep time, faint signatures preserved against all odds in a world transformed by billions of years of geological change. In our patient search for these whispers, we honor both the scientific method and the profound questions that drive human curiosity about our place in the cosmos, our relationships with other possible forms of consciousness, and our responsibilities as inheritors of intelligence in a universe that might be largely unconscious. Os's order on chaos creates patterns that stand out against the random processes of nature. On Earth, even our most ancient human settlements leave geometric traces visible from orbit. Stone circles, linear earthworks, regular spacing of settlements along rivers and coastlines. Martian geometric anomalies might take different forms, adapted to the planet's unique environment and the capabilities of whatever intelligence might have emerged there. Regular spacing of crater modifications, linear arrangements of geological features, geometric patterns in sediment deposits, artificial channeling of ancient water flows. The famous face on Mars in the Cydonia region captured public imagination precisely because it seemed to show geometric regularity, artificial symmetry. Higher resolution imaging has revealed it to be a natural formation, but the initial reaction was understandable. Our pattern-seeking minds are attuned to detect signs of intelligence, even where none exist. This phenomenon, called pareidolia, reminds us that we must be careful in our search for artificial patterns. The human mind excels at finding meaningful shapes in random configurations. Clouds that look like animals, rocks that resemble faces, geological formations that suggest artificial construction. Yet genuine artificial patterns do have characteristics that distinguish them from random formations. True geometric regularity, precise mathematical relationships, orientations that align with astronomical phenomena rather than prevailing winds or geological processes. If we found a series of circular formations, each exactly 100 meters in diameter, arranged in a perfect hexagonal grid across a Martian plain, aligned with the planet's magnetic field rather than its topography, we would have strong evidence for artificial origin. Such patterns would be extraordinarily unlikely to arise through natural processes. Chemical anomalies might provide more reliable signatures. Industrial processes concentrate elements in ways that differ from natural geological processes. Mining operations leave distinctive signatures in the distribution of metals and minerals. Large-scale manufacturing creates chemical byproducts that persist in soils and sediments. On Earth, we can detect the signatures of ancient human metallurgy in ice cores dating back thousands of years. Lead pollution from Roman silver mines appears in Greenland ice. Copper smelting leaves traces in lake sediments across Europe. These signatures persist because they represent artificial concentrations of elements that would be dispersed much more evenly by natural processes. Martian chemical anomalies might take different forms. Unusual concentrations of rare earth elements in sediment layers. Artificial isotope ratios that differ from natural nuclear processes. Organic compounds that exist in combinations never seen in purely geological contexts. The organic molecules already detected in Martian rocks show complexity that raises intriguing questions. Some of these molecules form naturally through interactions between water, minerals, and organic compounds delivered by meteorites. But others might represent something more interesting. Biological processes create organic molecules with specific handedness, favoring left-handed amino acids and right-handed sugars. Finding such asymmetries in Martian organics could indicate biological origin. If we discovered organic compounds with the opposite handedness from Earth biology, it might suggest an independent origin of life, a separate evolutionary pathway that made different fundamental choices. Energy signatures offer another possible trace of ancient intelligence. Large-scale energy use leaves distinctive patterns. Heat anomalies from concentrated energy production. Artificial modification of natural energy flows. Electromagnetic signatures from technological processes. Modern Mars shows intriguing thermal anomalies in some regions. Localized warm spots that don't correlate with known geological activity. These could represent natural hydrothermal systems, subsurface water reservoirs, or residual heat from impact events. But they could also indicate ongoing energy production from artificial sources. Underground modifications might provide the most durable signatures of ancient intelligence. Excavated chambers, artificial cave systems, underground water management systems, all could potentially survive surface erosion while preserving clear evidence of artificial origin. Ground-penetrating radar from orbital platforms has revealed complex subsurface structures across Mars. Most of these represent natural geological features, lava tubes, sediment layers, buried impact craters. But some anomalies remain unexplained, showing geometric regularity or structural complexity that doesn't fit obvious geological explanations. The polar layered deposits contain millions of years of accumulated sediments, creating the most complete climate record in the solar system. Within these layers, we might find evidence of artificial climate modification, atmospheric engineering, or large-scale environmental projects that altered the planet's atmospheric composition. Dust layers in the polar deposits could preserve signatures of massive construction projects, industrial activities, or environmental catastrophes. On Earth, volcanic eruptions create distinctive signatures in ice cores. Nuclear weapons testing has left radioactive markers in sediments worldwide. Similar signatures might exist in Martian polar ice, recording the activities of ancient civilizations. Biological modifications present another category of possible traces. If intelligence emerged on Mars, it might have modified local ecosystems, created artificial organisms, or left behind biological signatures in the form of preserved genetic material. Recent discoveries of DNA preservation in extreme environments on Earth suggest that genetic material might survive much longer than previously thought possible. In permanently frozen environments, protected from radiation and chemical degradation, DNA can potentially remain intact for millions of years. Martian permafrost might preserve biological materials from the planet's earlier, more hospitable periods. If intelligence emerged during these periods, it might have left biological traces preserved in the deep frozen soil layers that blanket much of the planet's surface. Artificial structures adapted to Martian conditions might take forms we haven't considered. Perhaps subsurface civilizations developed building techniques based on excavation and reinforcement rather than construction and assembly. Perhaps they learned to work with Mars's unique geology, creating structures that blend seamlessly with natural formations while serving artificial purposes. Consider the possibility of biological architecture, structures grown rather than built. Intelligence might have modified organisms to create living buildings, transportation systems, or manufacturing facilities. Such biological technology would leave different signatures than mechanical technology, but might be better adapted to Mars's harsh environment. The search for these traces requires patience, sophisticated instrumentation, and careful analysis. Distinguishing artificial signatures from natural anomalies demands detailed understanding of Mars's geological processes, atmospheric chemistry, and biological possibilities. As you rest tonight, imagine the patient work of detection unfolding across decades and centuries. Each new mission to Mars carries instruments more sensitive than the last, capable of detecting subtler anomalies, analyzing smaller samples, resolving finer details in the planet's complex history. Perhaps tomorrow's discoveries will reveal clear evidence of artificial patterns, chemical signatures that can't be explained by geology alone, structures that bear the unmistakable hallmarks of intelligence. Or perhaps we will find that Mars's anomalies all have natural explanations, that intelligence never emerged on our neighboring world. Either answer would be profound. Evidence of ancient Martian intelligence would revolutionize our understanding of life's possibilities in the universe. Evidence of Mars's sterility would emphasize the preciousness of consciousness and the remarkable chain of circumstances that led to its emergence on Earth. The traces we seek are whispers from deep time, faint signatures preserved against all odds in a world transformed by billions of years of change. In our patient search for these whispers, we honor both the scientific method and the profound questions that drive human curiosity about our place in the cosmos. Chapter 6: Tools of Discovery. How we search today we hold eyes that see beneath the dust and mechanical hands that touch the rocks. This is how we search for ancient echoes. Our exploration of Mars represents one of humanity's greatest technological achievements, an extension of human senses across the vast gulf of interplanetary space that transforms curious minds on Earth into explorers of other worlds. Each mission carries instruments more sophisticated than those available to previous generations, tools capable of detecting signatures that would have remained invisible just decades ago, technologies that push the boundaries of what we can observe, measure, and understand about planetary environments. The story of our search begins in orbit, with spacecraft that circle Mars like patient sentinels, studying every square kilometer of the planet's surface in exquisite detail that rivals the best geological surveys of Earth. These orbital platforms provide the global perspective necessary to identify patterns, anomalies, and relationships that would be invisible to surface-based observers, creating comprehensive maps that guide our understanding of Martian geology, climate history, and potential for ancient complexity. The Mars Reconnaissance Orbiter carries the high-rise camera, a technological marvel capable of resolving features smaller than a dining table from an altitude of 300 kilometers, providing images with resolution that exceeds anything available for most of Earth's surface. Through this electronic eye, we have mapped ancient river channels with clarity that reveals individual boulders in their beds, identified mineral deposits that record specific episodes in the planet's climate history, and traced the geological narratives written in cliff faces and crater walls across billions of years. High-rise images reveal Mars as a world of staggering geological complexity and beauty that rivals anything found on Earth. Canyon systems that dwarf Earth's Grand Canyon stretch across continents, their layered walls recording millions of years of environmental change in sequences more complete than any terrestrial archive. Ancient impact craters preserve evidence of bombardments that occurred when the solar system was young and chaotic, their pristine preservation telling stories of a world where geological activity ceased before erosion could erase the signatures of cosmic violence. Layered deposits record millions of years of climate history in sedimentary sequences that provide unprecedented detail about planetary environmental evolution. Each layer represents a specific period in Mars's past, a chapter in the story of atmospheric change, volcanic activity, and the gradual transformation from a world that might have harbored life to the frozen desert we observe today. But visible light imaging, remarkable as it is, represents only the beginning of our sensing capabilities, the foundation upon which more sophisticated analysis builds our understanding of planetary composition, structure, and history. The electromagnetic spectrum extends far beyond human vision, carrying information about chemical composition, mineral structure, and physical properties that require specialized instruments to detect and interpret. The CRISM spectrometer on the same spacecraft analyzes reflected sunlight across hundreds of wavelengths, identifying minerals with extraordinary precision that rivals laboratory analysis of hand samples. It can detect clay deposits that formed in ancient lakes, revealing not just their presence but their specific composition, formation temperature, and the chemical conditions of the waters that created them. Sulfate minerals that crystallized from evaporating seas tell stories of climate change and atmospheric evolution. Organic compounds preserved in billion-year-old rocks provide tantalizing hints about the chemical complexity that existed during Mars's most habitable period. Spectroscopic analysis operates on the principle that different molecules absorb and reflect light in characteristic patterns that serve as unique fingerprints. Each mineral, each organic compound, Each type of rock creates distinctive absorption features that can be identified through careful analysis of reflected sunlight. The technique is so sensitive that it can detect mineral concentrations as low as a few percent, revealing the presence of materials that would be invisible to conventional photography. This capability has revolutionized our understanding of Martian surface composition, revealing a chemical complexity that exceeds anything anticipated by early planetary scientists. The surface is not uniformly oxidized rust, but a complex mixture of minerals that record different episodes in the planet's history, different environmental conditions, different chemical processes that operated across geological time. Subsurface radar systems peer beneath Mars's surface with electromagnetic waves that penetrate several kilometers into the planetary interior, revealing hidden layers and buried structures that provide crucial information about geological history and subsurface conditions. The SHARAD radar can map underground formations with resolution measured in meters, creating three-dimensional images of buried impact structures, ancient lava flows, and sedimentary deposits hidden beneath newer formations. These subsurface maps show vast deposits of buried ice that represent the largest water reservoirs on the planet, underground glaciers that preserve evidence of climate conditions very different from those that exist today, ancient impact structures hidden beneath volcanic deposits reveal the intense bombardment that characterized the early solar system. Complex layering in polar deposits preserves the most complete climate record available anywhere in the solar system. Radar analysis has revealed that Mars's subsurface is far more complex and dynamic than surface observations alone would suggest. Underground water persists in unexpected locations. Buried landforms preserve evidence of geological processes that operated billions of years ago. Subsurface structures show geometric relationships that require careful analysis to distinguish natural formations from potentially artificial modifications. The orbital perspective provides global context that guides the selection of landing sites and exploration targets. But understanding Mars's potential for ancient intelligence requires close examination of specific locations where the most promising evidence might be preserved. This is where our robotic explorers become extensions of human curiosity, carrying increasingly sophisticated laboratories to the Martian surface and bringing human-level analytical capabilities to bear on questions that can only be answered through direct contact with alien materials. The Curiosity rover, active since 2012, represents a revolution in planetary exploration that transforms our approach to studying other worlds. Its analytical laboratory can determine the composition of rocks and soils with precision that rivals Earth-based facilities, bringing capabilities that previously required sample return missions directly to the Martian surface. The mobile laboratory concept allows detailed analysis of multiple sites across extended exploration campaigns that build comprehensive understanding of local geology and chemistry. The ChemCam laser spectrometer exemplifies the technological sophistication of modern planetary exploration, vaporizing tiny portions of rock from distances up to 7 meters, and analyzing the elemental composition of the resulting plasma through spectroscopic techniques. This remote analysis capability allows rapid survey of geological formations, identification of interesting targets for more detailed study, and creation of chemical maps that reveal the distribution of elements across Martian landscapes. Each laser pulse removes less than a microgram of material, creating a tiny pit barely visible to the naked eye, but the plasma created by vaporization contains atoms in excited states that emit light at characteristic wavelengths. Spectroscopic analysis of this light reveals the elemental composition of the target material with precision that approaches laboratory-quality analysis. The SAM instrument suite represents perhaps the most sophisticated chemical laboratory ever sent to another planet, capable of detecting organic molecules at concentrations measured in parts per billion, isotopic ratios that reveal ancient environmental conditions, and atmospheric compositions that provide clues about planetary evolution. The instruments can identify specific organic compounds, distinguish between biological and geological sources of carbon, and provide detailed information about the chemical environment that existed when the samples formed. Each sample that Curiosity analyzes adds detail to our understanding of Mars's ancient environment, building a comprehensive picture of the conditions that existed during the planet's most habitable period. The rover has confirmed that Gale Crater once contained a lake that persisted for millions of years, providing stable aquatic environments where complex chemistry could operate over extended periods. It has detected complex organic molecules in rocks formed during Mars's most hospitable climate period, compounds that might represent preserved biological materials or sophisticated geological chemistry. It has measured seasonal variations in atmospheric methane that suggest active processes continuing today, contemporary activity that might represent ongoing geological processes, or potentially even surviving biological systems. The methane detections are subtle and variable, requiring careful analysis to distinguish instrumental effects from genuine atmospheric phenomena, but they represent one of the most intriguing discoveries of the current exploration program. The Perseverance rover, exploring Jezero Crater since 2021, carries even more advanced instruments specifically designed to search for signs of ancient life and potential intelligence. Its pixel spectrometer can map the distribution of elements within rock samples at microscopic scales, revealing chemical variations that might indicate biological activity, artificial modification, or unusual geological processes. The Sherlock instrument uses ultraviolet lasers to detect organic compounds and minerals associated with biological processes, techniques that can identify molecular signatures invisible to other analytical methods. Ultraviolet spectroscopy is particularly sensitive to aromatic organic compounds, molecular structures that are common in biological systems and might be preserved in ancient Martian rocks. But Perseverance's most important capability may be its sample collection system, the first successful implementation of precision sample gathering for eventual return to Earth. For the first time in planetary exploration, we are gathering carefully selected Martian rocks and sediments that will be analyzed using laboratory techniques impossible to duplicate on Mars, potentially revealing subtle signatures of ancient biological activity that remain undetectable by current rover instruments. The samples collected by Perseverance come from the delta deposits of Jezero Crater, one of the most promising locations for preserving evidence of ancient life or even intelligence. The fine-grained sediments of this ancient river delta provide ideal conditions for concentrating and preserving organic molecules, creating natural archives that might contain the chemical signatures of ancient biological processes. Each sample tube represents a time capsule from Mars's ancient past, preserving materials under conditions that minimize contamination and degradation. The sampling process itself requires extraordinary precision, identifying the most promising targets, drilling cores that preserve geological context, sealing samples in ultra-clean containers that prevent contamination, and storing them under conditions that will preserve their integrity during the long journey to Earth. Ground-penetrating radar systems on both Curiosity and Perseverance reveal subsurface structure and composition that provide crucial information about geological history and potential artificial modifications. These instruments can detect buried layers that record ancient environmental conditions, underground water or ice deposits that might support contemporary life, and subsurface cavities that might represent natural caves or artificial excavations. The radar data provide three-dimensional maps of the subsurface environment that reveal hidden complexity beneath the dusty surface. Buried channel systems record ancient water flow patterns. Subsurface ice deposits preserve evidence of climate change across geological time. Underground structures show geometric relationships that require careful analysis to distinguish natural formations from potentially artificial features. Future missions will carry even more sophisticated tools that push the boundaries of planetary exploration toward capabilities that approach those of terrestrial geological and archaeological surveys. The upcoming Mars Sample Return campaign will bring Perseverance's collected samples to Earth laboratories, where they can be analyzed using techniques that represent the current limits of analytical chemistry, molecular biology, and materials science. Mass spectrometers capable of detecting individual molecules will search for organic compounds at concentrations far below current detection limits. Electron microscopes that can resolve cellular structures will examine samples for preserved biological materials. DNA sequencers might identify genetic material that has survived in frozen environments for billions of years. Isotopic analysis will provide unprecedented detail about ancient environmental conditions and potential biological processes. Drill systems under development will reach deeper into Mars's subsurface than ever before, accessing environments that have remained undisturbed since the planet's ancient past. Current rovers can penetrate only a few centimeters into rock surfaces, sampling materials that have been exposed to surface weathering and potential contamination. Future missions will drill meters or even kilometers into the subsurface, reaching pristine materials that preserve the most complete record of ancient conditions. Deep drilling will access subsurface water systems that might harbor contemporary life, underground ice deposits that preserve ancient atmospheric compositions, and buried sedimentary sequences that record complete environmental histories. These deep samples will provide unprecedented insight into Mars's evolution and potential for supporting complex chemistry across geological time. Advanced life detection instruments represent another frontier in our search capabilities, combining multiple analytical techniques to search for the complex patterns that characterize biological activity rather than looking for individual molecular signatures. These systems recognize that life creates statistical patterns, isotopic signatures, and chemical relationships that are different from purely geological processes. The search for technosignatures requires different tools than the search for biological signatures. Instruments designed to detect artificial materials, geometric patterns, and energy signatures that might indicate intelligent modification of planetary systems. Electromagnetic surveys can identify artificial materials buried beneath the surface, using their distinctive electrical and magnetic properties. Magnetometers can detect magnetic anomalies that might represent artificial structures or modified geological formations. Seismic instruments can distinguish artificial cavities from natural geological features through their acoustic properties. One of our most powerful tools for detecting artificial patterns is statistical analysis of high-resolution imagery, using machine learning algorithms trained to recognize geometric regularity, mathematical relationships, and organizational patterns that distinguish artificial structures from natural formations. These computer systems can analyze millions of images, identifying subtle patterns that human observers might miss, while avoiding the false positives that result from our tendency to see meaningful patterns in random data. Machine learning systems are becoming increasingly sophisticated at recognizing anomalies in planetary data, processing vast datasets from orbital surveys to identify locations that warrant closer investigation. They can recognize patterns too subtle for human detection, distinguishing artificial signatures from natural variations with increasing accuracy as they are trained on larger datasets and more sophisticated examples. The integration of multiple datasets provides the most powerful approach to detecting signs of ancient intelligence, combining information from orbital imagery, spectroscopic analysis, radar mapping, and ground truth from rovers to build comprehensive understanding of specific locations. Each type of measurement provides a piece of the puzzle that contributes to overall interpretation of geological history and potential artificial modifications. Orbital imagery identifies geometric anomalies and unusual surface features. Spectroscopic data reveals chemical compositions that might indicate artificial concentration of materials. Radar data maps subsurface structures that could represent natural caves or artificial excavations. Ground truth from rovers confirms or refutes interpretations based on orbital data while providing detailed analysis of local materials and structures. Each type of measurement provides an independent test of hypotheses about artificial origin. Geometric patterns visible in orbital imagery might represent natural geological processes, until chemical analysis reveals artificial concentrations of rare elements at the same locations. Subsurface anomalies detected by radar might appear geological until high-resolution imaging reveals artificial regularity in their structure and organization. The search for ancient Martian intelligence thus becomes a patient process of accumulating evidence, building cases based on multiple independent lines of investigation that converge on specific locations or phenomena. Single anomalies can almost always be explained by natural processes that we understand incompletely. But when multiple types of evidence point toward the same conclusions, when geometric patterns coincide with chemical anomalies and subsurface structures, the case for artificial origin becomes increasingly compelling. Our current capabilities represent only the beginning of what will be possible in coming decades as technology continues to advance, and our understanding of planetary processes becomes more sophisticated. Future missions will carry laboratories more advanced than any currently deployed on Mars, artificial intelligence systems that can analyze data in real time, and direct instruments toward the most promising targets, and coordinated fleets of rovers and aircraft that provide comprehensive surveys of selected regions. Advanced drilling systems will access the deep subsurface environments where evidence of ancient life or intelligence might be best preserved, protected from surface weathering and radiation that could destroy delicate signatures. Underground missions will explore cave systems and lava tubes that could preserve artifacts protected from surface erosion. Sample return missions will bring back not just individual rocks, but core samples from deep drilling that capture complete records of Mars's environmental history. The ultimate goal is comprehensive understanding that integrates all available evidence into coherent models of planetary evolution, climate change, and the potential for complexity to emerge under conditions very different from those that characterize modern Earth. We seek to reconstruct Mars's complete environmental history, to understand how its climate evolved from potentially habitable conditions to the harsh environment we observe today, to determine whether life emerged and how it might have developed across geological time. Within this broader understanding, we search for the subtle signatures that might indicate intelligence, complexity, civilization. The search is not separate from general planetary science, but represents the most sophisticated application of our analytical capabilities to questions that touch the deepest aspects of existence, consciousness, and our place in the cosmic order. As you rest tonight, consider the remarkable fact that human curiosity has reached across the void to touch another world, extending our senses through robotic explorers that serve as extensions of human consciousness operating in environments no human has ever experienced directly. Our robots are humanity's ambassadors to other worlds, carrying not just instruments but human dreams, questions, and the irrepressible desire to understand our place in the universe. Each day brings new data from Mars, new discoveries that reshape our understanding of planetary evolution and biological possibilities, new insights that guide our search for signs of complexity beyond Earth. The patient accumulation of measurements, the careful analysis of samples, the integration of multiple datasets all contribute to an emerging picture of Mars's deep history that grows more detailed and sophisticated with each passing year. We stand at the threshold of discoveries that could revolutionize our understanding of life's prevalence in the universe, intelligence's emergence from matter, and our own cosmic significance. The tools we have deployed and those we are developing provide unprecedented capabilities for detecting even subtle signatures of ancient complexity, chemical fingerprints of biological processes, geometric patterns that suggest artificial origin. Whether we find evidence of Martian intelligence or confirm Mars's sterility, the search itself represents one of humanity's greatest adventures, pushing the boundaries of technology, knowledge, and imagination in pursuit of answers to our most profound questions. In reaching toward Mars, we reach toward understanding of intelligence itself, consciousness as a cosmic phenomenon, and the responsibilities that come with being thinking beings in a universe that might be largely unconscious. Ground-penetrating radar systems on both Curiosity and Perseverance reveal subsurface structure and composition. These instruments can detect buried layers, underground water or ice deposits, and subsurface cavities that might represent natural caves or artificial excavations. The radar data provide three-dimensional maps of the subsurface environment, revealing hidden complexity beneath the dusty surface. Future missions will carry even more sophisticated tools. The upcoming Mars Sample Return campaign will bring Perseverance's collected samples to Earth laboratories, where they can be analyzed using techniques impossible to implement on Mars. Mass spectrometers capable of detecting individual molecules, electron microscopes that can resolve cellular structures, DNA sequencers that might identify preserved genetic material. Drill systems under development will reach deeper into Mars's subsurface than ever before. Current rovers can penetrate only a few centimeters into rock. Future missions will drill meters or even kilometers into the subsurface, accessing environments that have remained undisturbed since Mars's ancient past. Advanced life detection instruments represent another frontier in our search capabilities. These systems combine multiple analytical techniques to search for the complex patterns that characterize biological activity. They look not for individual molecules, but for the statistical patterns, the isotopic signatures, the chemical relationships that distinguish biology from geology. The search for technosignatures requires different tools than the search for biological signatures. Electromagnetic surveys can detect artificial materials buried beneath the surface. Magnetometers can identify magnetic anomalies that might represent artificial structures or modified geological formations. Seismic instruments can distinguish artificial cavities from natural geological features. One of our most powerful tools for detecting artificial patterns is statistical analysis of high-resolution imagery. Artificial structures and modifications typically show geometric regularity, mathematical relationships, and organizational patterns that differ from natural formations. Computer algorithms can analyze millions of images, identifying subtle patterns that human observers might miss. Machine learning systems are becoming increasingly sophisticated at recognizing anomalies in planetary data. These systems can process vast datasets from orbital surveys, identifying locations that warrant closer investigation. They can recognize patterns too subtle for human detection, distinguishing artificial signatures from natural variations with increasing accuracy. The integration of multiple datasets provides the most powerful approach to detecting signs of ancient intelligence. Orbital imagery identifies geometric anomalies. Spectroscopic data reveals chemical compositions. Radar data maps subsurface structures. Ground truth from rovers confirms or refutes interpretations based on orbital data. Each type of measurement provides a piece of the puzzle. Geometric patterns visible in orbital imagery might represent natural geological processes, until chemical analysis reveals artificial concentrations of rare elements. Subsurface anomalies detected by radar might appear geological until high-resolution imaging reveals artificial regularity in their structure. The search for ancient Martian intelligence thus becomes a patient process of accumulating evidence, building cases based on multiple independent lines of investigation. Single anomalies can almost always be explained by natural processes. But when multiple types of evidence converge on the same locations, when geometric patterns coincide with chemical anomalies and subsurface structures, the case for artificial origin becomes increasingly compelling. Our current capabilities represent only the beginning of what will be possible in coming decades. Future missions will carry laboratories more sophisticated than any currently deployed on Mars. Artificial intelligence systems will analyze data in real time, directing instruments toward the most promising targets. Coordinated fleets of rovers and aircraft will provide comprehensive surveys of selected regions. Advanced drilling systems will access the deep subsurface environments where evidence of ancient life or intelligence might be best preserved. Underground missions will explore cave systems and lava tubes that could preserve artifacts protected from surface erosion. Sample return missions will bring back not just rocks, but core samples from deep drilling that capture complete records of Mars's environmental history. The ultimate goal is comprehensive understanding. We seek to reconstruct Mars's complete environmental history, to understand how its climate evolved, to determine whether life emerged and how it might have developed. Within this broader understanding, we search for the subtle signatures that might indicate intelligence, complexity, civilization. As you rest tonight, consider the remarkable fact that human curiosity has reached across the void to touch another world. Our robots are humanity's extended senses, allowing us to see, touch, taste, and analyze environments that no human has ever experienced directly. Each day brings new data from Mars, new discoveries that reshape our understanding of planetary evolution and biological possibilities. The patient accumulation of measurements, the careful analysis of samples, the integration of multiple datasets all contribute to an emerging picture of Mars's deep history. We stand at the threshold of discoveries that could revolutionize our understanding of life's prevalence in the universe. The tools we have deployed, and those we are developing, provide unprecedented capabilities for detecting even subtle signatures of ancient complexity. Whether we find evidence of Martian intelligence or confirm Mars's sterility, the search itself represents one of humanity's greatest adventures. In reaching toward Mars, we reach toward answers to our most profound questions about cosmic loneliness and the nature of intelligence itself. Chapter 7. Scenarios of disappearance forces, slow or sudden, transformed a living landscape into silence. Let us follow them gently. The Mars we see today tells a story of dramatic transformation, of a world that changed from something hospitable to something harsh across the vast expanses of geological time. Understanding how this transformation occurred helps us comprehend what might have been lost in the transition, what traces might remain of more complex periods in the planet's history, and what lessons this holds for understanding planetary evolution and the fragility of habitable environments throughout the universe. The story begins with Mars's magnetic field, that invisible shield that once protected the planet's atmosphere from the steady erosion of solar wind. Deep within young Mars, a molten iron core generated powerful magnetic fields that extended far into space, creating a protective magnetosphere that deflected the charged particles streaming outward from the Sun in an endless river of plasma and radiation. This magnetic protection was crucial for maintaining atmospheric density and composition. Without a magnetic field, solar wind gradually strips away a planet's atmosphere, molecule by molecule, in a process so slow that it's invisible on human timescales but inexorable across geological eras. The charged particles from the Sun interact with atmospheric gases, transferring energy that allows lighter molecules to escape to space at rates that accumulate dramatically over millions of years. The magnetic field data recorded by orbiting magnetometers tells us that Mars once possessed a global magnetic dynamo comparable in strength to Earth's current field, possibly even stronger and more complex in its structure. This protective envelope was generated by convection in the planet's molten core, driven by heat from radioactive decay and residual energy from the planet's formation. But planetary magnetic fields are not permanent features. They depend on maintaining the specific conditions necessary for dynamo action. A molten, electrically conducting core with sufficient convection to generate the fluid motions that create magnetic fields. As planets cool, these conditions gradually disappear, and the protective magnetic envelope weakens and eventually vanishes. Sometime between 4.0 and 3.7 billion years ago, Mars's magnetic field began to weaken as the planet's core cooled and solidified. The internal heat engine that drove magnetic field generation was running down as radioactive decay decreased, and the planet radiated its formation energy into space. The protective magnetic envelope grew thin and patchy, leaving the atmosphere increasingly vulnerable to solar wind erosion. As the magnetic shield weakened, atmospheric erosion accelerated in a feedback process that made the loss increasingly rapid. Solar wind began stripping away the lighter atmospheric constituents first: hydrogen, helium, water vapor, and carbon dioxide. The loss of greenhouse gases reduced the atmosphere's ability to trap heat, cooling the surface and causing more water vapor to condense and freeze, further reducing atmospheric pressure. We can measure this process today through direct observation of atmospheric escape. Mars continues to lose atmosphere to space at a rate of about 100 grams per second, a process that seems trivial on human timescales, but represents enormous losses accumulated over geological time. This ongoing escape rate, measured by instruments on orbiting spacecraft, allows us to calculate backward and estimate the total atmospheric loss since the magnetic field disappeared. The calculations suggest that Mars has lost an atmosphere that might once have been as thick as Earth's, possibly even thicker during periods of intense volcanic outgassing. The lost atmosphere would have been capable of supporting liquid water across much of the planet's surface, maintaining greenhouse conditions that could have supported complex chemistry and potentially life for hundreds of millions of years. The loss was not uniform or steady. Computer models of atmospheric evolution suggests that Mars lost its atmosphere in stages, with periods of rapid loss alternating with more stable intervals when volcanic activity or other factors temporarily replenished atmospheric gases. During the rapid loss phases, the climate would have changed dramatically within relatively short geological periods, perhaps millions rather than hundreds of millions of years. These episodic changes would have created severe stress for any life or intelligence that had adapted to stable long-term conditions. Organisms or civilizations that evolved during periods of atmospheric stability would have faced sudden environmental challenges as pressure dropped, temperatures plummeted, and surface water began to freeze or boil away depending on local conditions. As the atmosphere thinned, surface pressure dropped below the point where liquid water could remain stable over most of the planet's surface. Water began to freeze or sublimate directly to vapor, depending on local temperature conditions. The hydrological cycle that had sustained rivers and lakes for hundreds of millions of years began to break down as the physical conditions necessary for stable surface water disappeared. But atmospheric loss was not the only force reshaping Mars during this critical period. The planet's geological activity was also declining as its interior cooled, and the driving forces for volcanism and tectonism weakened. Volcanic eruptions that had once released gases to replenish the atmosphere became less frequent and less massive. The global climate system that had maintained habitable conditions for so long began to fail as both internal and external energy sources diminished. The massive shield volcanoes that dominate the Martian landscape today were built during this transition period, representing the planet's last major episodes of volcanic activity. Olympus Mons, the largest volcano in the solar system, grew to its current enormous size through countless eruptions that occurred as the planet's climate system was collapsing. These eruptions temporarily thickened the atmosphere with volcanic gases, creating brief periods of enhanced greenhouse warming. But volcanic activity follows the same cooling trend that affected the magnetic field. As the planet's interior cooled, the magma production that feeds volcanic systems decreased. The volcanic outgassing that had helped maintain atmospheric pressure for billions of years gradually diminished, and atmospheric losses to space began to exceed replenishment, initiating an irreversible decline toward the thin atmosphere of modern Mars. Impact events added sudden punctuation marks to this gradual decline, creating dramatic but temporary changes in atmospheric conditions. Large asteroid or comet impacts could temporarily thicken the atmosphere by vaporizing surface rocks and ice, creating episodes of intense greenhouse warming that might have briefly restored surface habitability. The Hellas Basin, Mars's largest impact crater, was created by an object perhaps 100 kilometers in diameter that struck the planet during its early history. The impact would have temporarily created an atmosphere thicker than Earth's today, composed of vaporized rock and superheated steam. The energy released would have been equivalent to billions of nuclear weapons, creating a global catastrophe that reshaped atmospheric chemistry and climate. But these impact-generated atmospheres would have been unstable, much of the added material escaping to space within a few million years. The temporary thickening might have created brief windows of renewed habitability, followed by even harsher conditions than before, as the artificial atmosphere dissipated and surface pressure dropped below previous levels. Such impacts might have created cycles of renewed habitability, followed by environmental catastrophe that would have challenged any life or intelligence that had adapted to stable long-term conditions. The sudden environmental upheavals could have driven rapid evolutionary change or extinction, depending on the adaptive capacity of existing organisms or civilizations. Climate oscillations driven by orbital variations added another layer of complexity to Mars's environmental history. The planet's axial tilt varies much more dramatically than Earth's, swinging from nearly upright to tilted more than 60 degrees from vertical over periods of millions of years. These variations drive major climate changes that redistribute ice between polar and equatorial regions, while altering atmospheric circulation patterns and seasonal cycles. During high obliquity periods when Mars's axis is tilted far from vertical, the polar ice caps partially sublimate, releasing water vapor and carbon dioxide that thicken the atmosphere and allow more active weather systems. These periods might temporarily restore conditions favorable for surface water and biological activity. During low obliquity periods when Mars's axis is nearly upright, most atmospheric water condenses at the poles, creating a thinner, colder atmosphere with reduced weather activity. These cycles continue today, but their effects were more dramatic when Mars retained a thicker atmosphere that could respond more dramatically to orbital forcing. For any complex life or intelligence that might have existed during Mars's more hospitable period, these climate oscillations would have presented both challenges and opportunities. Periods of thicker atmosphere might have allowed expansion into new territories and the development of more sophisticated technologies. Periods of thinner atmosphere might have forced retreat to protected environments and the development of survival strategies adapted to harsh conditions. The gradual transition from surface habitability to subsurface refuge represents one of the most plausible scenarios for the survival of Martian complexity. As surface conditions became increasingly hostile, life might have retreated underground, finding stable conditions in deep aquifers and geothermal systems that remained buffered from surface climate change. Earth's subsurface biosphere demonstrates that life can persist in underground environments for millions or billions of years. Microorganisms living kilometers beneath the surface derive energy from chemical reactions between water and rock, reproducing slowly but persistently, while creating ecosystems that remain stable across geological timescales. These deep biosphere communities are completely independent of surface conditions, sustained by chemical energy sources that operate continuously regardless of atmospheric or climate changes. If life emerged on Mars during its more hospitable surface period, the planet's gradual environmental decline might have created strong evolutionary pressure for adaptation to subsurface conditions. Organisms that could survive underground would have had enormous advantages as surface habitability decreased. Natural selection would have favored traits that enabled survival in low-energy, chemically reducing environments. If intelligence emerged on Mars before surface conditions became hostile, it might have faced a choice between extinction and adaptation to subsurface environments. An intelligent species might have been uniquely capable of engineering solutions to environmental challenges, creating artificial habitats that could sustain complex life underground while surface conditions deteriorated. Underground civilizations could potentially survive dramatic surface climate changes while maintaining technological capability and cultural continuity. Protected from radiation, temperature extremes, and atmospheric loss, subsurface environments offer stability that surface environments cannot match during periods of planetary environmental change. Geothermal energy provides a power source that remains constant across millions of years, independent of solar variations, atmospheric changes, or surface climate conditions. Chemical energy from water-rock interactions offers additional energy sources that can sustain complex technological processes. Underground water systems provide the solvent necessary for biological and technological processes. The volcanic activity that characterized Mars's early history would have created extensive cave systems, lava tubes, and underground chambers that could have provided ready-made habitats for life retreating from increasingly hostile surface conditions. These natural underground spaces could have been modified and expanded to create artificial environments capable of supporting complex communities. Evidence for such subsurface refuge might remain detectable today through careful analysis of underground structures, chemical signatures of long-term biological or technological activity, and thermal anomalies indicating artificial energy use in subsurface installations. Advanced ground-penetrating radar systems might detect artificial modifications to natural cave systems. Geochemical analysis might reveal chemical signatures of long-term biological activity in underground environments. Another scenario involves partial adaptation to changing conditions, rather than complete retreat underground. Martian intelligence might have developed technologies for surviving in the transitional environment that existed as Mars's climate deteriorated. Atmospheric processors that could concentrate and recycle atmospheric gases. Enclosed habitats that could maintain habitable conditions independent of external atmosphere. Underground agriculture systems that could produce food using artificial light and recycled nutrients. Such adaptation might have bought time, allowing civilization to persist through the worst of the climate transition while developing more sophisticated survival technologies. But ultimately, the fundamental energy budget of a cooling planet works against maintaining complex surface activity. Even the most sophisticated technology requires energy, and energy sources become increasingly limited as geological activity declines and atmospheric protection disappears. The end, when it came, might have been sudden rather than gradual. A particularly large impact event, a massive volcanic eruption, or a severe solar storm during a period of weakened magnetic protection could have overwhelmed even well-adapted civilizations. The environmental changes that had been gradual might have accelerated suddenly, creating challenges that exceeded the adaptive capacity of existing technologies. Alternatively, the end might have been voluntary. A sufficiently advanced civilization might have recognized the inevitability of Mars's environmental decline and chosen to migrate elsewhere rather than face certain extinction, perhaps to Earth's early biosphere, carrying the seeds of life that would eventually evolve into terrestrial organisms, perhaps to environments in the outer solar system, where stable conditions could be maintained through technological means, perhaps beyond the solar system entirely to planets orbiting other stars. This possibility raises profound questions about our own origins and our relationship to potential Martian predecessors. If Martian intelligence predated Earth's biosphere, if panspermia carried life from Mars to Earth, then we might be the descendants of Martian civilization, the continuation of intelligence that first emerged under alien skies billions of years ago. The evidence for such possibilities remains subtle, ambiguous, open to multiple interpretations that require the most careful analysis and the most rigorous application of scientific methodology. But the questions are so profound that they justify the most comprehensive and sophisticated search possible, using all available technological capabilities. The search for signs of how Martian complexity might have ended becomes part of the larger search for signs that it ever existed. The scenarios of disappearance provide frameworks for understanding what kinds of evidence might remain, what signatures might persist, how to distinguish natural extinction from artificial migration, how to recognize the traces of civilizations that chose departure over adaptation. As you settle toward sleep, consider the vast scales of time and change that have shaped our neighboring world. The slow transformation from a hospitable planet to a frozen desert, the patient work of erosion that has obscured almost all traces of the ancient past. The remarkable persistence of clues that survive across billions of years to tell their stories to minds capable of reading them. Whether Mars once harbored intelligence or remained always sterile, its history offers profound lessons about planetary evolution, environmental change, and the fragility of habitable conditions. The forces that reshaped Mars continue to operate throughout the universe, affecting planets around other stars, determining the fate of worlds we will never see directly, but can understand through the example of our neighboring planet. In learning to read the story of Mars's transformation, we learn to better understand our own planet's future and the cosmic forces that shape the destiny of worlds. We develop appreciation for the remarkable stability that has characterized Earth's environment across the billions of years necessary for complex life to evolve. We gain perspective on the challenges that face any civilization, whether human or alien, that depends on planetary environments for its survival. The red planet serves as both laboratory and warning, a place where we can study the processes that determine whether worlds remain habitable or become sterile, whether complexity can emerge and persist, or is inevitably erased by the larger forces that govern planetary evolution. In understanding Mars's fate, we better understand the precious nature of the conditions that allowed consciousness to emerge on Earth, and the responsibility that comes with being thinking beings in a universe where thinking might be rare and precious. Chapter 8. Beyond the natural. Controversial theories. Some stories shine with mystery. Science invites us to see them with care. Throughout our exploration of Mars, certain discoveries have captured public imagination in ways that transcend their scientific significance. These controversial findings occupy a unique space in our understanding, representing the intersection between legitimate scientific inquiry and the human tendency to see patterns, purpose, and intelligence where none may exist. The most famous of these discoveries is the face on Mars, first photographed by the Viking 1 orbiter in 1976. The image showed what appeared to be a massive humanoid face carved into the surface of the Cydonia region, complete with eyes, nose, and mouth arranged in unmistakably facial proportions. For decades, this formation fueled speculation about ancient Martian civilization. Books were written, documentaries produced, theories developed about the artificial origin of the Cydonian complex. The face became a cultural icon, representing humanity's deep desire to find evidence of intelligence beyond Earth. Higher-resolution imaging from subsequent missions revealed the formation to be a natural mesa, sculpted by wind and erosion into a shape that triggers human pattern recognition from certain angles under specific lighting conditions. The face disappeared when viewed from different perspectives or under different illumination, revealing itself as a classic example of pareidolia, our tendency to perceive meaningful patterns in random stimuli. This revelation offers an important lesson about the nature of anomaly detection and the need for multiple independent confirmations of unusual discoveries. Science progresses through the careful testing of hypotheses, not through the preservation of appealing mysteries. Yet the face on Mars saga also demonstrates the value of public interest in unusual discoveries. The attention generated by the controversial image drove funding for higher-resolution imaging systems that revealed not just the natural origin of the face, but also genuine geological wonders throughout the Cydonia region. The pursuit of one mystery led to the discovery of many authentic marvels. Other controversial features have generated similar cycles of speculation and scientific investigation. Geometric patterns in crater formations, regular spacing of surface features, unusual erosion patterns that seem to suggest artificial modification of natural landscapes. Most of these anomalies have straightforward geological explanations when examined carefully. Mars's unique environment creates erosion patterns, crystal formations, and geological structures that can appear artificial to observers unfamiliar with Martian geology. The planet's thin atmosphere, extreme temperature variations, and unique mineral compositions produce features that have no close parallels on Earth. But the process of investigating these anomalies serves an important function in planetary science. Each investigation expands our understanding of Martian geological processes, atmospheric behavior, and environmental history. The search for artificial patterns, even when unsuccessful, teaches us to recognize the full range of natural phenomena that Mars can produce. Some discoveries remain genuinely ambiguous, open to multiple interpretations that cannot yet be definitively resolved with available evidence. These cases represent the frontier of our understanding, the boundary between what we know and what we suspect. Unusual mineral deposits in certain regions show concentrations and distributions that are difficult to explain through conventional geological processes. While these might represent natural phenomena operating under conditions unique to Mars, they might also indicate artificial concentration of materials through mining or industrial processes. Geometric patterns in sedimentary layers suggest possible artificial modification of natural depositional processes. Regular spacing, mathematical relationships between layer thicknesses, and orientation patterns that correlate with astronomical rather than geological phenomena all warrant careful investigation. Thermal anomalies detected by infrared sensors show localized heat sources that don't correspond to known geological activity. These could represent subsurface water reservoirs, residual heat from impact events, or radioactive decay in concentrated mineral deposits. But they could also indicate artificial energy production from subsurface installations. The key to evaluating such anomalies lies in developing multiple independent lines of evidence. Genuine artificial signatures should be detectable through several different types of measurement. Chemical composition should differ from natural formations. Geometric patterns should show mathematical precision. Subsurface structure should reveal artificial modification. Perhaps more importantly, artificial signatures should show evidence of intelligent design, purposeful modification serving recognizable functions. Random artificial patterns are no more meaningful than random natural patterns. Intelligence implies intention, planning, systematic modification toward specific goals. The search for such evidence requires sophisticated analytical techniques and careful interpretation. Computer algorithms can identify statistical patterns in large datasets that might escape human attention. Machine learning systems can recognize subtle anomalies that distinguish artificial signatures from natural variations. But the ultimate judgment about controversial discoveries must rest on the scientific method's most fundamental principle. Extraordinary claims require extraordinary evidence. The more dramatic the implications of a discovery, the more rigorously it must be tested, the more thoroughly alternative explanations must be explored. This principle protects science from the human tendency toward wishful thinking, while remaining open to genuine revolutionary discoveries. The history of science includes many cases where established theories were overturned by careful investigation of anomalous observations. The possibility of ancient Martian intelligence represents exactly the kind of extraordinary claim that demands extraordinary evidence. The implications would be so profound, the impact on human self-understanding so dramatic, that we cannot afford to accept such conclusions without the most rigorous proof. Yet we also cannot afford to dismiss unusual observations simply because they challenge conventional thinking. The balance between healthy skepticism and openness to new possibilities defines the essence of scientific inquiry. Current controversial theories about Mars span a wide spectrum of plausibility. Some, like the artificial origin of certain geological formations, remain within the bounds of scientific possibility while requiring additional evidence for confirmation. Others, like claims of artificial structures visible in low-resolution imagery, fail to withstand scrutiny using higher quality data. The most intriguing possibilities often lie in the borderland between different scientific disciplines. Biological signatures that might indicate geological processes. Geological formations that might represent biological activity. Chemical compositions that could result from either natural or artificial processes. Resolving these ambiguities requires interdisciplinary collaboration, bringing together expertise from geology, biology, chemistry, and planetary science. Each field contributes unique perspectives and analytical techniques that illuminate different aspects of complex problems. The future of controversial Mars research lies in developing more sophisticated detection methods and analytical techniques. Advanced spectroscopic systems can identify subtle chemical signatures that indicate artificial processes. High-resolution imaging can reveal geometric patterns too precise to result from natural phenomena. Most importantly, sample return missions will allow detailed laboratory analysis of materials from controversial locations. Techniques impossible to implement on Mars can be applied to carefully selected samples, revealing chemical and structural details that definitively distinguish artificial from natural origin. As you rest tonight, consider the delicate balance between skepticism and wonder that guides our exploration of Mars. We must remain open to extraordinary possibilities while insisting on extraordinary evidence. We must investigate unusual discoveries thoroughly, while avoiding the trap of seeing intelligence where none exists. The controversial theories surrounding Mars serve a valuable function in driving scientific progress, even when they prove incorrect. They focus attention on unusual phenomena, motivate development of better analytical techniques, and ensure that we do not overlook genuine anomalies in our eagerness to explain everything through conventional understanding. Whether the current controversies surrounding Mars ultimately reveal evidence of ancient intelligence or simply teach us more about the planet's remarkable geology, they contribute to our growing understanding of our neighboring world and the possibilities it may have harbored during its long and complex history. Chapter 9, Philosophy. What if Mars came before us? If our past was entwined with another world, our stories would change subtly, profoundly. The possibility that intelligence emerged on Mars before it appeared on Earth touches the deepest questions of human identity and cosmic significance. If this speculation proves true, it would not merely add another chapter to the history of the solar system. It would rewrite the fundamental narrative of consciousness itself. Consider the implications if we discovered that Mars harbored complex life, or even intelligence during the period when Earth was still dominated by simple microorganisms. Such a discovery would challenge our assumptions about the rarity of consciousness, the unique conditions required for its emergence, and our own place in the hierarchy of cosmic intelligence. The timeline makes this possibility particularly intriguing. Mars's most habitable period occurred between 4.1 and 3.7 billion years ago, when the planet maintained a thick atmosphere and stable surface water. During this same period, Earth was experiencing its late heavy bombardment, a time of intense asteroid and comet impacts that repeatedly sterilized much of the planet's surface. Life on Earth during this period was exclusively microbial, simple single-celled organisms eking out existence in a hostile environment subject to repeated catastrophic disruptions. Complex life would not emerge for another billion years. Intelligence would wait nearly 4 billion years more. If Mars's stable climate persisted for hundreds of millions of years, as geological evidence suggests, it provided a window of opportunity that Earth did not possess during the same period. A world with stable temperatures, flowing water, and protection from catastrophic impacts might have been the first place in our solar system where complexity could emerge and persist. This possibility raises profound questions about the relationship between planetary environments and evolutionary complexity. We tend to assume that Earth-specific conditions were necessary for the emergence of intelligence. But perhaps any stable, water-rich environment provides sufficient conditions for complexity to develop, given adequate time. The concept of panspermia adds another layer to these considerations. If life can travel between worlds on meteorites and asteroids, then the emergence of life on one planet might seed biological development throughout the solar system. Mars and Earth exchange material regularly through impact events that blast rocks from one world's surface into space, eventually delivering them to the other. During the period when Mars was most habitable, Earth was being heavily bombarded by asteroids and comets. Many of these impacts were powerful enough to blast Martian material into interplanetary space. Some of this material would inevitably have reached Earth, carrying with it any microorganisms that might have evolved in Mars's ancient oceans. If Martian life preceded Earth's biosphere, then we might be descendants of Martian organisms, children of a biological heritage that spans two worlds. Our cellular machinery, our genetic code, our fundamental biochemistry might all reflect choices first made under alien skies. This possibility transforms our understanding of human origins. Rather than being the unique products of Earth's particular evolutionary history, we might represent the continuation of biological complexity that first emerged on Mars, survived planetary catastrophe, and found refuge on a neighboring world that was just becoming hospitable to complex life. Even more provocatively, if intelligence emerged on ancient Mars, it might have actively guided its own survival through the transition between worlds. Perhaps the panspermia that seeded Earth's biosphere was not random, but directed, the result of deliberate choices made by minds that recognized their world's declining habitability. Such scenarios challenge our deepest assumptions about consciousness and continuity. If Martian intelligence preceded our own, we might be not the first thinking beings in our solar system, but inheritors of a cognitive legacy that stretches back billions of years. The philosophical implications extend beyond questions of origin to questions of destiny. If intelligence emerged twice in our solar system, it suggests that consciousness might be more common in the universe than we currently suppose. The conditions that give rise to thinking beings might be less rare, less dependent on precise environmental fine-tuning than our Earth-centric perspective suggests. Alternatively, if Mars harbored intelligence that subsequently vanished, it offers sobering lessons about the fragility of consciousness and the environmental threats that can terminate even advanced civilizations. The red planet becomes a monument to the vulnerability of intelligence, a reminder that thinking beings remain subject to forces beyond their control. The search for Martian intelligence thus becomes more than an archaeological expedition. It becomes a quest for understanding our own nature, our cosmic context, and our responsibilities as possibly the only current thinking beings in our local region of space. If we are alone, if Mars never harbored complexity beyond simple chemistry, then we bear unique responsibility for consciousness in our corner of the universe. Every decision we make about our planet's future, every step we take towards sustainability or destruction, carries weight that extends beyond our own survival to the continuation of intelligence itself. If we are not alone, if Mars once bloomed with thinking beings, then we are part of a larger story of consciousness in our solar system, We might be inheritors of wisdom, descendants of intelligence that faced and survived planetary catastrophe, carriers of cognitive traditions that stretch back to the earliest epochs of planetary history. Either possibility humbles human pretensions while elevating human responsibility. Whether we are the first intelligence in our solar system or inheritors of an ancient legacy, we face choices that will determine whether consciousness continues to flower or withers under the pressure of environmental change. The methods we develop to search for Martian intelligence also serve as practice for the greater search that awaits us among the stars. Every technique we refine for detecting subtle signatures of complexity on Mars prepares us for the eventual search for intelligence around other stars. The statistical frameworks we develop, the pattern recognition algorithms we design, the interdisciplinary collaboration methods we establish all contribute to humanity's growing capability for recognizing intelligence in environments very different from our own. Mars serves as a testing ground for techniques that will eventually be applied to exoplanets orbiting distant stars. But perhaps the most profound impact of discovering Martian intelligence would be its effect on human unity and perspective. The knowledge that thinking beings had emerged elsewhere would place human conflicts in cosmic context, emphasizing our shared heritage as conscious beings in a universe where consciousness might be rare and precious. Cultural differences that seem vast from our current perspective might appear trivial when measured against the gulf that separates thinking beings from unconscious matter. Political divisions that currently shape human affairs might recede in importance when viewed from the perspective of consciousness's cosmic rarity and fragility. The search for Martian intelligence thus becomes not just a scientific expedition, but a philosophical journey, an exploration of questions that touch the core of human meaning and purpose. Whether we find evidence of ancient complexity or confirm our cosmic solitude, the search itself transforms our understanding of consciousness and our place in the universe. As you drift toward sleep, consider the remarkable fact that minds capable of contemplating these questions have emerged from the chemistry of an ancient planet. Whether those minds first appeared on Earth or Mars, whether we are alone or part of a larger community of consciousness, the very fact that we can ask these questions represents one of the universe's most extraordinary achievements. In seeking signs of Martian intelligence, we seek not just knowledge about our neighboring world, but understanding of intelligence itself. We explore not just planetary history, but the deepest mysteries of consciousness, meaning, and cosmic purpose that define the human experience of existence. Chapter 10. Planetary Archaeology. Future methods and ethics to explore is to care, to touch without destroying, to look without erasing. The search for evidence of ancient Martian intelligence requires the development of entirely new scientific disciplines, methodologies that blend traditional archaeology with planetary science, astrobiology, and advanced materials analysis. We stand at the threshold of becoming a spacefaring civilization, and with that capability comes the responsibility to explore with wisdom and restraint. Planetary archaeology faces challenges that terrestrial archaeology never encounters. The time scales involved dwarf anything in human experience. The environments are hostile to both human explorers and delicate instruments. The evidence we seek has been subjected to billions of years of erosion, radiation, and chemical alteration. Yet these challenges also create opportunities. The vacuum of space preserves materials that would have long since decayed in Earth's active biosphere. The lack of plate tectonics on Mars means that ancient surfaces remain accessible rather than being subducted into the planet's interior. The thin atmosphere provides clear visibility across vast distances, allowing orbital surveys of unprecedented resolution. Future missions to Mars will carry archaeological tools adapted to planetary exploration. Ground-penetrating radar systems capable of mapping subsurface structures to depths of kilometers. Precision drilling equipment that can extract core samples without contaminating them with terrestrial materials. Portable analytical laboratories capable of detecting single molecules of organic compounds. The integration of artificial intelligence with these instruments will revolutionize our ability to recognize patterns and anomalies. Machine learning systems trained on vast databases of geological formations will be able to identify structures that don't fit natural patterns. Computer vision algorithms will analyze millions of high-resolution images, flagging geometric regularities that might indicate artificial origin. Robotic excavation systems will allow careful exploration of promising sites without the contamination risks associated with human presence. These systems will combine the precision of surgical robots with the durability required for planetary exploration. They will be capable of exposing and documenting potential artifacts while preserving the archaeological context that gives meaning to individual discoveries. Sample return missions represent the ultimate tool for planetary archaeology. Materials brought back to Earth can be analyzed using techniques impossible to implement on Mars. Electron microscopy can reveal cellular structures preserved in ancient rocks. Mass spectrometry can detect molecular signatures at concentrations measured in parts per trillion. Genetic sequencing might identify preserved DNA or RNA from ancient biological systems. But the most sophisticated technology means nothing without careful attention to the ethics of planetary exploration. Mars is not merely a scientific laboratory, but potentially the grave of an ancient biosphere, possibly even ancient intelligence. Our exploration must be conducted with respect for what we might find and careful consideration of the rights of potential Martian life. Planetary protection protocols already govern our current missions to Mars, designed to prevent contamination of the planet with terrestrial microorganisms that might interfere with the search for indigenous life. Future archaeological missions will require even more stringent protocols, ensuring that our search for ancient intelligence doesn't destroy the very evidence we seek to find. The forward contamination of Mars with Earth life poses obvious risks to the integrity of any biological signatures we might discover. A single terrestrial microorganism could multiply and spread, creating false positive signals that might be mistaken for evidence of Martian biology. Worse, terrestrial life might destroy genuine Martian biological materials, erasing evidence that has survived for billions of years. But back contamination represents an equally serious concern. If Mars harbors life, even simple microbial life, in its subsurface environments, bringing Martian materials to Earth could introduce alien organisms to our biosphere. While the probability of such organisms being harmful to Earth life is low, the consequences could be catastrophic if they prove capable of surviving and reproducing in terrestrial environments. The ethics of planetary archaeology extend beyond practical concerns about contamination to deeper questions about the rights of potentially intelligent beings. If we discovered evidence of ancient Martian intelligence, what obligations would we have to respect their cultural legacy? How should we balance scientific investigation with preservation of potentially sacred sites? These questions become even more complex if we consider the possibility that Martian life or intelligence might persist in subsurface environments. Our drilling operations could inadvertently breach underground ecosystems that have remained isolated for millions of years. Our sample collection could disturb civilizations that have retreated from the hostile surface to find refuge in the stable subsurface environment. The development of protocols for first contact with subsurface Martian intelligence represents one of the most complex challenges facing future planetary exploration. How do we distinguish between simple microbial life and genuine intelligence? How do we establish communication with beings that might have evolved under radically different environmental pressures? How do we ensure that our first contact doesn't inadvertently destroy the civilizations we're trying to understand? International cooperation will be essential for addressing these challenges. The exploration of Mars and the search for ancient intelligence affects all of humanity, not just the nations capable of mounting interplanetary missions. The protocols we establish, the discoveries we make, and the decisions we face will shape humanity's relationship with potential cosmic neighbors. Legal frameworks for planetary archaeology remain largely undeveloped. Current space law treats celestial bodies as the common heritage of mankind, but it provides little guidance for situations involving indigenous life or intelligence. We need new legal structures that balance scientific exploration with protection of potential alien rights. The training of planetary archaeologists will require integration of multiple disciplines, rarely combined in traditional education. These explorers must understand geology and biology, chemistry and physics, archaeology and anthropology, ethics and law. They must be capable of making complex decisions under extreme conditions while maintaining scientific rigor and ethical sensitivity. Remote operation capabilities will be crucial for much of this work. The communication delays between Earth and Mars make real-time control impossible, requiring autonomous systems capable of making complex decisions without human intervention. These systems must be programmed with both scientific protocols and ethical constraints, ensuring that they pursue discovery while respecting potential alien rights. The public engagement aspects of planetary archaeology cannot be ignored. The discovery of evidence for ancient Martian intelligence would be one of the most significant events in human history, requiring careful communication to ensure accurate understanding and appropriate response. The media protocols, educational programs, and public discussions surrounding such discoveries must be planned in advance. Cultural sensitivity will be particularly important if we discover evidence of Martian intelligence. Different human cultures will interpret such discoveries through their own philosophical and religious frameworks. Some may see confirmation of cosmic brotherhood. Others may perceive threats to established beliefs. Managing these diverse responses, while maintaining scientific objectivity, will require unprecedented international cooperation. The long-term implications of planetary archaeological discoveries extend far beyond Mars itself. The methods we develop, the protocols we establish, and the ethical frameworks we create will guide humanity's exploration of other potentially habitable worlds. Every choice we make in exploring Mars sets precedents for our eventual exploration of exoplanets around other stars. As you settle into rest tonight, consider the weight of responsibility that comes with the capability to explore other worlds. We are potentially the first generation of humans capable of detecting signs of alien intelligence, and possibly the last generation with the opportunity to find evidence of ancient complexity in our solar system. The choices we make about how to conduct this search will define not just what we discover, but who we become as a spacefaring civilization. The balance we strike between curiosity and caution, between investigation and preservation, between human interests and potential alien rights, will shape humanity's cosmic legacy. In developing the tools and protocols for planetary archaeology, we prepare not just for discoveries about Mars, but for humanity's eventual role as explorers of the galaxy. The wisdom we develop in searching for our first cosmic neighbors will guide us when we eventually encounter intelligence among the stars. Chapter 11. Closing Reflection. Science and wonder. We have walked through memories and possibilities. Now everything settles like dust in the evening light. As our journey through Mars's mysteries draws to a close, we find ourselves enriched by questions as much as by answers. The red planet has shared its secrets reluctantly, revealing layer by layer the story of a world transformed, a climate lost, and possibilities that may forever remain tantalizingly beyond our complete understanding. What have we learned from this gentle exploration? We have discovered that Mars was once a world where water flowed freely, where complex chemistry flourished, where the ingredients for life and perhaps even intelligence existed in abundance for hundreds of millions of years. We have seen how geological processes preserve memories across billions of years, creating archives more complete and enduring than any library built by human hands. We have explored the tools and methods by which we search for signs of ancient complexity, the patient accumulation of evidence that gradually builds our understanding of planetary history. Each rover track across Martian soil, each orbital survey of canyon walls, each chemical analysis of ancient rocks adds another piece to a vast puzzle that spans geological ages. The evidence we have found remains tantalizingly ambiguous. Organic molecules that might represent ancient biology, or might result from purely geological processes. Geometric patterns that could indicate intelligence, or could reflect the mathematical regularities inherent in natural phenomena. Chemical signatures that might preserve the fingerprints of ancient life, or might simply record the complex chemistry of a dynamic planet. This ambiguity is not a failure of our scientific methods, but a reflection of the profound challenges involved in detecting subtle signatures across billions of years of geological time. The processes that preserve evidence also obscure it, creating a palimpsest where new stories are written over old ones, where interpretation requires the most careful analysis and the most rigorous skepticism. Yet in this uncertainty lies profound beauty. We have learned that the universe is far more complex and subtle than our ancestors imagined. We have discovered that planets have histories as rich and detailed as any human civilization. We have found that the chemistry of life connects worlds across the vast distances of space, creating possibilities for biological kinship that transcend planetary boundaries. The philosophical implications of our search extend far beyond the specific question of Martian intelligence. In learning to read the stories written in stone, we have developed new ways of understanding time, change, and the persistence of information across cosmic scales. We have gained appreciation for the remarkable fact that the universe preserves records of its own history, encoding in minerals and isotopes and geological formations the evidence needed to reconstruct events that occurred when our solar system was young. Our search has taught us humility about the limits of knowledge, while demonstrating the power of careful observation and patient analysis. We have learned to distinguish between what we know with confidence and what we suspect with varying degrees of certainty. We have developed comfort with uncertainty, recognition that some questions may remain forever beyond definitive resolution, while still being worthy of investigation. The search for ancient Martian intelligence has also revealed the importance of interdisciplinary collaboration in addressing the most profound questions. Geology and biology, chemistry and physics, archaeology and anthropology all contribute essential perspectives to understanding planetary history. No single discipline possesses all the tools needed to read the complex stories preserved in Martian rocks. Perhaps most importantly, our exploration of Mars has expanded our definition of what it means to be alive, what it means to be intelligent, what it means to be significant in a cosmic context. We have learned to think in scales that dwarf human experience, while maintaining appreciation for the subtle processes that create complexity from simplicity. Whether or not Mars ever harbored intelligence, our search has transformed human consciousness. We are no longer a species confined to a single world, but cosmic explorers capable of extending our senses across interplanetary distances. We have developed technologies that allow us to touch other worlds, analyze their chemistry, and read the stories preserved in their rocks. This expansion of human capability comes with expanded responsibility. As we develop the tools to detect intelligence on other worlds, we must also develop the wisdom to respond appropriately to what we might find. The protocols we establish for planetary exploration, the ethical frameworks we develop for potential contact with alien intelligence, will shape humanity's cosmic legacy. The techniques we have developed for searching Mars will soon be applied to other worlds in our solar system and eventually to planets orbiting other stars. Every method we refine, every analytical technique we perfect, every pattern recognition algorithm we develop contributes to humanity's growing capability for detecting complexity in environments far from Earth. The statistical approaches we use to distinguish artificial signatures from natural phenomena will guide our analysis of data from increasingly powerful telescopes capable of studying the atmospheres and surfaces of distant worlds. The interdisciplinary collaboration methods we have pioneered will be essential for interpreting discoveries that challenge our understanding of life's possibilities. In this sense, Mars serves as a stepping stone to the stars, a testing ground for technologies and methodologies that will eventually be applied across the galaxy. Every mission to Mars prepares us for the greater explorations that await among distant suns. But perhaps the most valuable outcome of our search has been the refinement of wonder itself. We have learned to marvel at the complexity that emerges from simple ingredients given sufficient time and suitable conditions. We have developed appreciation for the remarkable fact that matter can organize itself into patterns capable of contemplating their own existence. The organic molecules detected in Martian rocks, whether they represent ancient biology or complex geology, demonstrate that the universe naturally tends toward chemical complexity under the right conditions. The river valleys and lake beds carved into Martian stone show that worlds can sustain conditions suitable for life across geological time. The very fact that we can read these stories shows that intelligence, once emerged, can expand its understanding across cosmic distances. Our exploration of Mars has revealed a universe rich with possibility, where the ingredients for complexity are abundant, where time and space provide endless opportunities for matter to explore new forms of organization. Whether life is common or rare, whether intelligence is widespread or precious, the cosmos clearly provides the stage for remarkable emergent phenomena. The red planet has served as our teacher, showing us how to read the deep history encoded in rocks and minerals, how to detect subtle signatures of ancient environments, how to balance skepticism with openness to extraordinary possibilities. These lessons will guide us as we extend our search to other worlds and eventually to other star systems. As we continue our patient exploration of Mars, we do so with enhanced appreciation for both the power and the limits of scientific inquiry. We understand that some questions may require decades or centuries to answer definitively. We have learned to value the journey of discovery as much as any specific destination. The search for ancient Martian intelligence thus becomes more than an archaeological expedition. It becomes a meditation on the nature of consciousness, the meaning of intelligence, and the responsibilities that come with the ability to contemplate our place in the universe. Whether we eventually find clear evidence of Martian complexity, or confirm that Mars remained always sterile, our search will have succeeded in expanding human understanding and preparing our species for its role as cosmic explorers. In reaching toward Mars, we reach toward answers to our deepest questions about existence, meaning, and our place among the stars. The mysteries of Mars will continue to unfold as our technologies advance and our understanding deepens. Each new mission will carry more sophisticated instruments, more refined analytical techniques, more nuanced approaches to distinguishing artificial signatures from natural phenomena. But the greatest discoveries may not be specific artifacts or definitive proof of ancient intelligence. They may be the gradual accumulation of understanding about how planets evolve, how life emerges and persists, how intelligence develops and spreads, how conscious beings relate to the cosmos that gave them birth. In this ongoing exploration, we honor both the scientific method and the sense of wonder that drives human curiosity. We pursue knowledge with rigor while remaining open to possibilities that challenge our current understanding. We seek answers while treasuring the questions that make us human. Chapter 12. Epilogue. Returning to the room, breathe, let the planet drift away in the distance and allow your body to rest. As our journey through Martian time draws to its gentle close, we return to this moment, to this quiet space where you rest, to the familiar rhythm of breath and heartbeat that connects you to the endless cycles of life. The red planet recedes now into the realm of contemplation, carrying with it all the questions we have explored together. The ancient rivers that once carved channels through alien landscapes. The mysteries preserved in stone across billions of years. The possibilities that hover at the edge of knowledge, neither confirmed nor dismissed, waiting patiently for future discovery. Let your breathing slow and deepen. Feel your body settling into complete relaxation as the vastness of cosmic time expands around you. The urgency of immediate concerns fades in the perspective of geological ages. The complexities we have contemplated dissolve into the simple peace of present awareness. Notice how your breath mirrors the patient rhythms that have shaped worlds across the eons. Each inhalation draws in molecules that have participated in countless cycles of creation and transformation. Each exhalation releases them to continue their eternal journey through time and space. The dust particles floating in the air around you have traveled distances measured in astronomical units. Some may have originated in distant stars, others in the solar wind that strips atmospheres from planets, still others from the gradual erosion of mountains and continents. You breathe the cosmos with every breath. The questions we have explored tonight about ancient Mars, about the possibility of intelligence among the stars, about our place in the cosmic story, these questions need not be answered tonight. They are companions for the long journey of human understanding, not puzzles to be solved before sleep. Let them rest now in the deeper mind, where patient contemplation works below the level of conscious awareness. The same processes that preserve memories in stone across billions of years also preserve wonder and curiosity in the human spirit across generations. Feel your muscles releasing their tension as you settle more deeply into rest. Your arms growing heavy as Martian gravity. Your legs sinking into the soft surface like rover wheels coming to rest after a long day's exploration. Your head cradling itself in the comfort of this moment. The boundary between waking and sleeping mirrors, the boundary between knowing and wondering that we have explored throughout our journey. Both transitions happen gradually, naturally, without force or urgency. Both lead to states of being that refresh and restore. As consciousness becomes dreamlike, you might find yourself walking again through those ancient Martian landscapes we have visited in imagination, standing beside rivers that flowed when the solar system was young, touching rocks that have waited billions of years to share their stories, breathing air thick with possibilities. These dream explorations continue the work of wonder that we have begun together. In sleep, the mind processes and integrates the day's experiences, creating new connections, new insights, new possibilities for understanding. Let sleep come naturally, without effort or intention. Like the formation of sedimentary layers on ancient Mars, it happens through patient accumulation, gentle deposition, the gradual settling of awareness into deeper rhythms. The stars that witnessed Mars's transformation from a blue-green world to the red planet we know today still shine in the darkness outside. They have seen the rise and fall of countless worlds, the emergence and extinction of innumerable possibilities. They continue their patient vigil, marking time across scales that dwarf all earthly concerns. You are part of this cosmic story, a brief flowering of consciousness in a universe that has been billions of years in the making. Your capacity for wonder, your ability to contemplate the deep history of other worlds, your participation in the search for cosmic companionship, all represent remarkable achievements in the evolution of matter toward consciousness. Rest now in the knowledge that this capacity for wonder is itself one of the universe's most extraordinary creations. The same forces that carved rivers on ancient Mars, that preserve memories in stone across geological time, that may have given birth to intelligence among the stars. These forces also created the human mind capable of contemplating such marvels. Sleep deeply, and let your dreams carry you to distant worlds where possibilities flourish in the spaces between knowing and wondering. Let the gentle rhythms of rest restore your spirit for tomorrow's explorations, whatever forms they may take. The red planet waits patiently in the night sky, holding its secrets close, ready to share them with minds curious enough to ask the right questions and patient enough to listen to whispers from deep time. Breathe slowly. Release completely. Rest deeply. The cosmos dreams through sleeping minds, and in your rest, you participate in the universe's long contemplation of its own magnificent possibilities. Sleep now, cosmic explorer. Mars will be there when you wake, carrying its mysteries forward through another day, another year, another eon of patient time. The search for ancient intelligence continues in the laboratories and mission control centers, where dedicated scientists work to expand human understanding. But tonight, it continues also in the quiet spaces of rest and dream, where wonder itself is renewed for the long journey ahead. Let consciousness fade like the last light of Martian sunset, gentle and gradual and complete. In sleep, you join the vast rhythms that connect all things across space and time, the cosmic dance that turns planets and shapes the destiny of worlds. Rest now. The universe continues its patient work of creation and discovery, and your part in that work is renewed each time you wake to wonder at the magnificent complexity of existence. Sleep deeply. Dream beautifully. Wake when you are ready to continue the eternal human journey toward understanding our place among the stars. The red planet holds its vigil through the night, carrying its memories forward through time, waiting for the next dawn of discovery to illuminate secrets preserved across the vast expanses of cosmic history. Sleep now, and let Mars and its mysteries settle into the deeper currents of awareness, where they will enrich your understanding and wonder for all the days to come.